Good afternoon. We welcome you all to this International Conference on Mathematical Advances and Applications 2020, dated for today and tomorrow. Hope all of you are doing good. Once again, we extend a warm welcome and an successful, informative, interactive conference these days. Today, we have in our midst Dr. Vijay Kumar from Manav Rachna University, Faridabad, Haryana, and Dr. T. Srinivas Rao from Adama Science and Technology University, Ethiopia, to speak to us. Thank you, sirs, for accepting our request and joining us to be a part of this conference and to extend the best of your expertise to our delegates. We do also have more than 10 presentations today from different delegates from various places of India and a special presentation from Nepal too. After the speakers speak, we'll have a discussion with the speakers. Anyone could interact with them, speak to them, clarify anything that you would like to, and make use of the experts who are joining us today. After the discussion, we'll have the paper presentations, and then at the end of the paper presentations, we will interact with each and every delegate and even the audience, participants and the paper presenters. You can interact with each one, seeking any clarifications or anything you would like to add, you may do so. We have many things to share with you, but on the online system, we would not like to waste any minute, and that's how we have asked your recorded presentations, and the same would be taken into consideration and they will be played. But you are all requested to be online, and if possible, kindly put on your videos on to maintain the decorum of the conference, and especially in interaction, I wish everyone to be online. And your attendance these 2 days is very important, and as you resubmit your college, the certificate that is being given will be duly considered as it is on par with any other conference like what we do offline. And tomorrow we have 2 more speakers to speak to us from NIT Uttarakhand and former professor in Malaysia and currently serving in India. They will be speaking to us. And tomorrow also similarly we'll have the paper presentations. Closer to 10 to 12 papers will be there tomorrow also. And after that we'll have certificate distribution. Your soft copy of certificates and proceedings and your hard copy proceedings and the publication details will be informed to you tomorrow during the valedictory session. We look for your cooperation, support, and your active interaction these 2 days in the conference. Once again, I thank you all for keeping your trust into IMRF and Red Talks and investing your work into this conference. And we promise you that these 2 days we will do the best to inculcate, to impart, to extend the best of the knowledge through our experts and during the interactive sessions too. Thank you all. We shall meet again once again. Thank you. We are privileged to have in our midst Dr. Vijay Kumar, Professor and Head Department of Mathematics, Manav Rachna International Institute of Research and Studies, Faridabad, Haryana, India. Dr. Vijay Kumar did his PhD in applications of generalized corpus entropy and institutic fuzzy sets in communication systems and medical diagnosis of headache under the guidance of Dr. Preeti Gupta, Professor Department of Statistics, Maharshi Dayananda University, Rohtak, Haryana. He did his MSc from Garhwal University, Srinagar, and diploma in mathematics from Allison, UK, and also diploma in statistics from Allison, UK. He has extensive knowledge in MATLAB, Skylab, and he has the practice of conducting the practical of numerical computing in C language. He did projects like developing virtual and physical teaching models for mathematics laboratory. Also worked in the project Sakshat funded by the Ministry of Human Resource Development, Government of India. He also served as an reviewer for Taylor and Francis Journal and also International Journal of Applied Physics and Mathematics. He holds to his credit two patents, delivered more than 9 invited talks, published more than 35 papers in the form of journals, books, and chapters in different proceedings. He has attended more than 20 international conferences, workshops, and he is a member on the board of many professional bodies. Dr. Vijay Kumar, a long associate of IMRF and Red Talks, a good friend of mine. So thank you for accepting our request in short notice and joining us. We always delight your presence and your talks, and this afternoon also we cherish the same and we request you to speak to our audience. Thank you very much, sir.
Hi everyone, this is Dr. Vijay Kumar from Manrachna International Institute of Research and Studies, Faridabad. So I welcome you all in this session on COVID-19 analysis and modeling. You all know pretty well that COVID-19, which is commonly known as coronavirus, so is in fashion these days. So everyone is discussing about coronavirus. In fact, we all talked about their implications in our routine life. It is no doubt that COVID-19 disturbed world economy, deliver recession, and almost every industry and an individual got affected by this virus. So the aim of today's session is not is only to aware you about the trajectory of the virus and its rate of the spread by some mathematical technique. So till date, COVID-19 witnesses more than 13 lakh deaths globally. So today's talk is not just discussing about the economy factor. We are not discussing about the recession and all that stuff. So it is only dedicated to the mathematical stuff, that how mathematics predict the spread of COVID-19. Okay, so that the authorities will make their self aware about that. So I'm starting my presentation. So this is the brief agenda of this presentation. So first of all, what I do, I will let you know about the basic preliminaries, what is spread of the disease, then how much population is affected by this COVID-19, and then my actual work will start. We collected data. We collected data through Kaggle, and the data from January 1, 2020 to May 31st, 2020, and we clean this data and clean this data, and actually we get the final data. So this final data is the data which we got after the pre-processing of this. Then we do the profiling of the data. So we do the profiling of the data by using Python. Python as a language here. Python we use here. Then we see the spread of the COVID-19. When we talk about the spread here, we select top 5 countries. So top 5 countries means till May 30, 2020, what was the top 5 countries where this COVID-19 affect more? So then we see the rate of change of cases of this, then we find the maximum infection rate. So when I talk about analysis, we also calculate a correlation matrix for that. So actually this correlation matrix contributes nothing in this analysis, but is just to analyze how to analyze the data among the scholars. So that's why I put this slide here. So then we calculate the actual R square values. Now, actual R square values are very less. Now here I am using the 2 mathematical models. These are 2 mathematical models. Basically, this is a one mathematical model. We use least square approximation method here. That is machine learning technique. We call it as a regression analysis method. So in this model number 1, we see the nature of the model, and then to see the nature of the growth of spread, and then accordingly we will select our model, mathematical model number 1, and then we take the output of the model number 1 values as my input, and then use model number 2. Okay, so these two I use Excel. We may also use Python for that. There is simple 2-line program for that. But here I am using Excel just to make you aware that Excel is also a tool. Those who don't know Python, they may also do their analysis from this Excel also. And finally, we will get the improved R square value, and then we go with the conclusion part. So this is the agenda of today's session. Now, when I switch to the COVID-19 spread, if you see, so this is a very simple trajectory. If you see the spread, how this disease is spreading, everyone says that we will go with the social distancing and put mask, X, Y, Z, lot of things. But see, this virus is spreading like anything. Okay, so social distancing or lockdown is not the solution because it affects a lot of things. Okay, it affects the human life in layman language, I can say. So this is my COVID-19 spread. So in layman language, I can say it spread like a web of, it spread like a web of a spider. Okay, its shape spread is like that. Now, how much population affected by COVID-19? More than million people are died till date, as the data is saying. So this is the COVID-19 death as on 15 May 2020. Okay, and before analyzing this data, first of all, see these bullets. So green, this blue one says that, so this is by world's population. This is my percentage of world's population. Right now, the total population of world is about 7.8 billion. Whole world population 7.8 billion. And the percentage of world annual death. So this is the actual death happened. The actual that happened basically. Okay, and this is the percentage of world COVID-19 deaths. So this is the last one is the world COVID-19 death. If you see, number of deaths are more in the US with respect to other countries. If you see India, COVID deaths are very less because of a number of reasons, maybe immunity factor, maybe the diversity of the environment, XYZ factor. We are not discussing that in this presentation. So this is a simple the disease that its implementation. No, this is my raw data. Data I took from Kaggle between January 1, 2020 to May 31st, 2020. So this is actual data. The data is simple. We got it in the CSV format. So total number of cases, new cases, total death, new death. So we only select the component that how many number of cases. We are talking about the new cases. How many number of cases are there? Okay, total number of cases. One number of cases are there in it. So in this context, we select 5 countries, top 5 countries: Brazil, Russia, Spain, UK, and US. So these are the 5 countries which are, according to the data, they are top 5 countries. They are top 5 countries as far as the spread of the disease is concerned. From 2020 first 20. So we took a data, but there are some zero values in these countries. So we clean this data we by using some data cleaning techniques, and ultimately we will get the data of 132 days 132 days in these 5 countries. So Brazil, Russia, Spain, UK, and US. So this is a format of the data. So we upload this format in the Python console, and I did the Python calculation through Google Collaboratory. It is a online platform used for that. So these 5 countries. Now the analysis of the component is given in the form of graphs. In the coming slide, we will discuss the graphs. So the profiling of the data. So I already explained you profile is done by the Excel. Sorry, not Excel, it is Python. See, so this is a profiling of Brazil. So I'm taking a profiling of 132 days. I already explained you. So see the trajectory of Brazil, how COVID is. See, it is 0 case till 61. Then they are increasing, and the growth is looks like something. It is exponential. You can say the growth is something like which is exponential. So this is a case for a Brazil. Again in Russia also, initial days again the profile is same 132 days. Initial days up to 60, 65 days. So not much cases, but the cases will rise exponentially. So if you see in Russia, the curve is more sharper than the curve of Brazil. Similarly, if I'm talking about the Spain, Spain is the data is very versatile. Versatile data. Initially, it go constantly cases, then it increase more steeply as compared to Russia, then increases exponentially, and then take a some certain shape where the cases are going to be neutral. They're going to be neutral. And then in UK also, the trajectory is more or like that of Russia. If you see the filing of the data, initially there are no cases. In the midway, if I'm talking about 0 to 60 days, 0 to 60 days means January 21st to next 60 days. So they have not like that, and then the profiling they are changing. This is for US also. So this is for US. Again, the profiling till mid 60 days, not much change, but after then they are increasing. See, they are increasing linearly. They are increasing exponential, but in linear form. It's steep, not taking a some slope, but stately they are increasing. Means the rate of increase is faster than that. So if what we get out from this profiling, if you see in this whole profiling, somehow the cases are increasing, but only in case of Spain, the cases are increasing, and then up to certain benchmark, they are going to be neutral. Okay. So why we take a question is why we are taking the data from this date to that date? Because if you see these from January 1 to May 30, this is May 31st. So this is a deciding number of cases. So this is a deciding factor. So this period is very critical period. In this period, we actually get the trajectory, approximate trajectory of the virus, whether this virus will increase at which rate, decrease at which rate. Okay, so we actually get the approximate nature of the virus during this period. So that's why we do our calculation till this date, because till this date, in some countries, they don't have the facility of this test also, like in India. Till this date, not more test was happened. uh, but we take the countries according to the data which are among the top most 5 countries. So India will come maybe in the last of the June. They come in a pool of top 5 countries. No, this is the trajectory of the all 5 countries. If you see in this all 5 countries, so the sudden increase is US. So this is my US. So this US is sudden increasing, and rest of the country more or less they are overlapping with each other. The number of cases are more or less same with each other. Now, how this disease is spreading? So what we do, we divide this 132 days. Okay, we divide this a period of 132 days into a interval of 33 days. We take 4 intervals. So first 33 days, next 33 days, then next, and then next 33 days. What is the nature of the disease? Okay, so again we just deep dive into the data and do minute just a interval of 33 days, means 1 month, approximately 1 month profiling. So for each country, again 5 country, we are doing the profiling like that. If you see in the first 33 days in Brazil, there are no case, no case. Okay, from January 21st to the next 33 days, no case. And then after 34, 64, the cases are increasing. Okay, they are increasing by some mood, very little mood. Okay, not, I can say, sharp, but in this short interval from 67 to 90 days, the trajectory shows that cases are increasing. They are increasing. They are increasing. Okay, they are increasing. And also in the fourth interval, the cases are increasing. Okay, so means in the first interval, Brazil, there are no case, no cases. Okay, there is no case. I tell you, January 21st means till the mid of till Feb, there was no case at all in Brazil. But from 1st of March, the number of cases are going to increase, and increase steeply, increase so frequently, rapidly, you can say. Then the next is a case of a Russia. Again, if you see in Russia, the first interval shows that there are not much cases, only 2 cases. Okay, so first there are 0, then 1, then only 2 cases between this period. Okay, but if I talk about second interval, in second interval, not much cases, but they are increasing. They are increasing. Okay, they are increasing. Okay, they are increasing. So in third interval also they are increasing. They are increasing like anything. Okay, but in fourth interval they increase so quickly. They increase so rapidly. If you see, so this graph shows that they are increasing so rapidly. So means fourth interval for every country. If we take this is very critical for the purpose of analysis. So first three are not okay, means the COVID, if we can say, the in this top in this the second country, it increases maybe in the last week of April, or in the month of May. They are increasing so quickly. The spread is so quick. Similarly, in case of Spain also, Spain, but in Spain, if you see second interval, the cases are more. In third interval, cases are increasing, but going to some neutral. So they got some break-even point, and after then the cases are decreasing. And in fourth interval, the cases are going to decrease. But if you see in Spain, the number of cases are increasing in second interval. So it is very critical for this. Okay. And in UK also, first interval, not much cases. In second interval, it is increasing. The trajectory is increasing. In third also, it is increasing. In fourth, there is some break even, and it is going to means decrease. So this is somehow you can say that it's concave curve. So it is going to something downward. Okay, so if the curve like this, they are some convex curves, so which are increasing mode. So this is somehow which after some break even, they will get some decrease in number of cases. Finally, in USA, you see in USA, uh, other than first and second interval, third and fourth interval, the cases are increasing like anything. And see the curve, cases are increasing like anything. So they are increasing. They are increasing. So they are in lakhs. They are in lakhs. 1.8. They are in lakhs. They are increasing like anything. Okay, so if we discuss minutely as per this, the day-wise spread or the intervening force spread, we saw that US, the number of cases are increasing so sharply. Now we come to the rate of change in the number of cases in COVID-19. So rate of change. This is a mathematical fundamental. Rate of change means derivative. What we get out from rate of change? Basically, we are getting the extreme number of cases. You can say the minimum or the maxima for that. So what would be the maximum cases in a day? Okay. And what would be the minimum cases in a day? But here we are not talking about minimum, we talked about only maximum number of cases. So we simply use the Python, the rate of change derivative tool there, and find the rate of change of cases. And if you see in case of Brazil, curve number 1, see this is the rate of change. This is the rate of change. Okay, fluctuation is there, but not much fluctuation. In case of Russia, see the curve is volatile curve. Okay, so not much peaks, means increase and decrease is not much. Number of cases or decreasing in very less mode, but increasing sharply. So in case of Spain also, initially they are increasing like anything, but after 61 days or this, they are decreasing in decreasing mode. So we saw this in previous curves also. So in case of UK also, number of cases are increasing and then finally they are decreasing. But in US, see the peaks are, see if you see the peaks, see the peaks. So there's a lot of gap between maximum and the minimum value. See, we're talking about in a day or 2-3 interval, number of cases are increasing and decreasing. And finally, they get some downward trend. They follow some downward trend in it, but still the number of cases are more. So from this rate of change, what we get? We will get the maximum infection rate, maximum number of cases. So first, in this context, we have a Brazil, 33,000 plus cases. We have Russia, 11,000 plus cases. We have Spain, 9100 cases. We have UK, 8700 plus cases, and US, 48,000 plus cases. So these are the maximum number of cases in a day, in a single day between this period. So these countries have maximum number of cases like this. And see US. US has 48,529. A single day between this period, they have 48,000 cases, and they are more. See, what is the population of USA? It is roughly about 33 crores. 33 crores. In India, it is one. We are 138 crores. We are 4 times more than US. Okay, and see that how the virus spread there and how the virus spread in our country. Okay, so this is very critical period. I already told you. So this period is mainly for the researchers who took this period and take this data for future perspective. Means if you take the data after this period, you will get maybe you get the information that how cases are decreasing. But in this period, cases are more or less increasing, not decreasing. Some countries are decreasing, but in some countries they are steepest, I can say. This is the maximum infection rate that we again calculated using Python. So this is a correlation matrix. I already told you that this correlation has no relevance in this work. Just I say analysis. You guys must know in some data we check the correlation. This is a COVID data, but we don't check the whether the country to country correlation or not. There is no relevance. Okay, the relationship correlation is only established when there is a relationship between the variables. So we don't say that Spain has some relationship with that. So the relationship can only be happen because if those countries are dependent on each other, they have some human transfer between that we are not taking here. We are not right now discussing, but just to showcase you the that by Python we can also find the correlation for a data. But here this metric has no relevance. I'm just showcase. You can check what is the Brazil with some other country, and that is Russia. What is Brazil correlation of Brazil with Spain? This you can say Russia. This is Spain. This is UK. This is USA, and this is Brazil. Okay. So my point is here only to say that by Python we can do analysis. So I motivate you to learn Python. This is a very good mathematical language. This is good for data analysis. Moreover, this is open source because SPSS and other languages like MATLAB, they are paid. Okay. And paid means they are beyond reach. You can say very costly. Python is open source. You can use this tool and do a lot of analysis on that. So this is my actual root mean square value, R square value. So this R square value again I calculated through Python. Simple one line code you write, you will get the R square value of your data. So this is 0.68, 0.69, 0.86, 0.82, 0.83. What is R square root mean square value? So root mean square value is um, is basically used in certain experiments where you ensure that my readings or my data, my information, what you got from that experiment is correct or not. R values, it is basically the RMS, root mean square of exact value minus approximate value, square and under root of that value. So it should be less than. So it the good your score is that the value should be near to 1 or 0.9 above. It will also work, but this value is very less. Value is very less means lot of errors are there. So we try to clean our data. Try to clean our data in this respect and use certain mathematical mode. So if we're talking about some COVID mode, so a lot of mathematical models are already into. One is SIR model, SEIR model. then SEIRD. I means susceptible, infectious. Okay, like this. Okay, so this is basically SER, but this SIRD model, it depends upon one thing, that is reproductive number. I have one more. I did work initially in SEIR model. I use some online calculator to calculate that, and there we consider the R. R means reproductive number. Reproductive number means one infectious person will infect roughly 2.4 people. This is, you can say, RO. If RO is less than 1, it means disease is no more infectious. But in case of COVID in country like China, the RO is somewhere more than 7. If you see, there is one cruise, I forgot the name, that is the Princess, something like that. The passenger who are traveling in the cruise at that point of time, they tested, when they tested, all, maybe 100 something persons are there, only except 3 4 all, but so there we can say reproductive number is 7. Scientists calculate that it is 7, 4 also in some countries, but if it is less than 1, then it means disease is no more infectious. But still this is infectious, so the RO depend upon country to country, it is more or like that. So initially when the COVID came, it says that the initially RO is 2.4. It infects 2.5 roughly percent. Okay, but no, it says that it infects more like anything. So that's why scientists, they don't even bother or try to calculate this RO. So these SIR, SCIR, SIRD model has certain implications. So these are differential equation based models, means they are time dependent models. So they are deterministic in nature. They are not stochastic. And they can't act well when we have data. Okay, because when we have data, it means some initial values are given. No doubt these models are used to calculate, to predict the values, but they, for that you need to use some different interface. For that you calculate the model, you write a code to solve these models, and your data is accordingly as per this model also. You must have RO, you must have the initial infection rate, and the 10 number of things you initially must know to calculate this model. This model will not work for raw data, like the data which we get out from Worldometer, the data which we get out from in India, Arogya Setu, the government website, from any XYZ website, we get the data. So that is basically generalized data. And if you see that, if you see the Worldometer or COVID, any dashboard, you will see there are a lot of curves are given, and that curves are due to regression. That's why I choose to apply the regression tool. Okay. So first model is this. So this is my first mathematical model. So see, the nature of data is exponential. I know my nature of data is exponential. So that's why. So I choose this proposed model. This is of exponential nature. Y is equal to AVX, which is of exponential in nature. Okay. Y is equal to AVX. So these are the normal equations for this. Okay, so n means my number of days, and number of days I am taking 132 days. Okay, so xi means my day number 1, day number 2, day number 3. So this is my day number, and this is y is the number of days. Okay, so this is a normal equation. So where capital Y, it has certain significance because it is very difficult to calculate this model. So this is basically, you can say, log transform. You can also call this model a log transformation. You can search in Google. You will get some log transform models also. So means that when I use this model, on the given data, what data I already show you for different countries, for a country number, for Brazil, for Spain, for UK, for Russia, for US. So I use this model and I calculate this thing in Excel. Okay, I calculate this in Excel. I can also calculate this thing in Python also, the single 1-2 line code, but just to apprise you about this Excel, so that's why I'm taking. Okay, so when I use this thing and actually I will get this value for Brazil. My this my fitted values are this. For Russia, for Spain, for UK, for US, my fitted values are this. Okay, so these values, by using these values, by these fitting values, so we can predict. But still, when I calculate, my R score will not good. So that's why what I do, whatever fitted value I will get out from this data, I will use, I will embed those values in my next model, next mathematical model. And that model is again a model of the same category, but it is a polynomial of order 3. You can say cubic polynomial. If you see the shape of the curve, no doubt the growth is exponential look like, but somehow they are cubic. Somehow at a certain steep they are cubic. Okay, so that's why I choose to take some cubic this polynomial. So when I use this cubic polynomial, so these are the normal equations. So in undergraduate course in numerical analysis or in some statistical techniques method, so this method is already taught in undergraduate and postgraduate, any who have mathematics subject with them. So these are the normal equations. So when I solve these normal equations, I will get the value of A, B, C, and D. And ultimately, so this is a fitted value for Brazil, for Russia, for Spain, for UK, for US. Okay. So I simply put the number of days in this, I will get the approximate number of patient. Okay, sorry, approximate number of infectious person with COVID-19. Simply I put the value of X, 133 days, 134 days, 135 days, and so we will get a very accurate value. So this accurate value, accurate value we know when we get the R score. And see the R score what we are getting here, that is near to 1. It is near to 1. It is 0.9, 0.98, 0.99, 0.94. If R square is greater than 0.9, then you can say your that is approximate and the actual values don't have much difference in that. So this is my actual study of just analysis and my model this data. So this is a need of the day that we just calculated. From this study, we just see that my residual is minimum. Residual means my error. So what least square method is the basic principle of this, that we minimize error. Okay, so because when we say that approximate and accurate value, so we minimize the error. So when we minimize the error, we talked about this this R square. We calculate the R square values. So you can use this study for other diseases also if data is too available. You can use these methods for other kind of problems where you have some data and you need to do prediction. Actually, this least square technique, this is called the regression technique. So regression technique is basically used in machine learning. In machine learning for continuous data, you can use discrete, but for continuous data, machine learning technique used to do the prediction for that. So this is a very good model. You can use this model to predict anything like that. You can predict if some scholars are doing PhD, they collect the data, and their PhD work is analyze the data, study it, and comes out with some beautiful results, and they publish those results very remarkably. So in that way, if they want to predict that we took a sample of say 200 and so values and then predict for that. So in that context also we need this least square method is very useful tool for. So these are the set of references that we use. Actually, COVID-19 till at that time no work was published. We simply go to the Google sources. We see the biology of the COVID-19, how COVID-19 affect economy, how COVID-19 deliver recession and all that stuff. So we do literature review of some other infectious diseases and make up our mind to tune our study in this way. And we took the data from Kaggle data sources. Any questions from your side? So I welcome you all for that. Even I love to answer your questions. If you do ask some relevant questions to me. And these are my details. You can write me or you can contact me at these numbers. So I will make available you there also. Okay. So this is all from my side. This is all from my side. Thank you very much.
We have in our midst Dr. Srinivas Rao Tota, Department of Applied Mathematics, School of Applied Natural Sciences, Adama Science and Technology, University, Ethiopia. Dr. Srinivas Rao Tota, currently working as an assistant professor in Adama Science and Technology University, did his PhD from Motilal Nehru National Institute of Technology, NIT Allahabad, did his MSc from Indian Institute of Technology, IIT Madras, and completed his graduate studies from Andhra College, Vijayawada. His main research interests focus computer algebra, mathematical modeling, numerical analysis, etc. He is a member board on many technical program committees and professional bodies of international repute. He is an editorial board in many overseas and international journals, to mention a few from Pakistan, Singapore, etc. He is expertised in Maple, C, MATLAB, Mathematica. He has published more than 36 papers and delivered more than 21 invited talks on various international platforms. Thank you very much, sir, for accepting our kind request and joining us in spite of your busy schedules. We love to hear you, sir. Kindly speak to our audience now. Thank you, sir.
To all, I am Dr. Srinivas Tota from Adama Science and Technology University. In this talk, we are going to discuss about maple implementation of a reduction algorithm for differential algebraic equations. Before going to start, I would like to thank the organizers for giving me this opportunity. So in this talk, we mainly focus on implementation of the reduction algorithm in Maple. The outline of the presentation is as follows. We start with introduction and we recall the reduction algorithm for differential algebraic system with an example, and then we focus on the implementation of the algorithm in Maple. We give also pseudocode of the algorithm with sample competitions, and finally we have some references. In introduction part, we will start with a matrix differential system. ADU plus BU is equal to F, where A and B are coefficient matrices and D is a differential operator and F is a forcing function. So in detail, where Z is a complex variable, AZ and BZ are m by n matrices of analytic functions, and F of Z is a m-dimensional vector analytic function, and U of Z is a n-dimensional unknown vector which is going to be determined. That is the solution of the given system of equations. And D is a differential operator, that is D is equal to D over dz. And based on the coefficient matrix A of Z, we will differentiate the matrix differential system. That is, for example, if A is a non-singular matrix, that is regular matrix, then the system of equations in equation 1 are turn out to be a ordinary differential equation. And system of first order ordinary differential equation can be solved easily, and there are many methods also available in the literature. Suppose A is a non-singular and M is not equal to N, then this system is turned out to be a system of differential algebraic equations. Suppose A is equal to 0 matrix, then it turn out to be a system of algebraic equations, and there are many methods available how to solve a system of algebraic equations. Since we are focusing on system of differential algebraic equations, so the coefficient matrix A of Z should be a singular matrix and M is not equal to N. Then the system of equations in equation 1 turn out to be a system of differential algebraic equations. And there are many applications available in science and engineering where the coefficient matrix A is singular and M is not equal to N. So that is only here mentioned. Many scientists and engineers have been studied differential algebraic systems intensively from a numerical point of view as well as the analytical point of view, and they developed new approaches to solve the system of differential algebraic equations. Some others use a notation of differential indices, and some others solve DAEs using the technique of reduction algorithm. And in our talk, we are going to focus on solve the system of differential algebraic equations by using reduction algorithm. So, since we are focusing on operator notation, we can represent a given system of differential algebraic equation in operator notation, that is LU is equal to F, where L is a matrix differential operator, that is L is equal to AD plus B. A is a coefficient matrix, A and B are coefficient matrices, and D is a differential operator, and overall L is a matrix differential operator, and F is a forcing function that will be given in the problem, and we have to calculate the value U. So we recall the reduction algorithm now. Since we are not very much focusing on what is the algorithm involving, but we are focusing on the implementation of this algorithm. Let K be a subfield of a complex number C. We everywhere we use K as a subfield of a complex number C. We denote ring of formal power series by K of Z in variable Z, and K of open brackets denote the quotient field, that is K of Z and Z inverse. The ring of differential operator denoted by K of Z and D with the coefficients in K of Z. In this talk, we consider system of following form: AD plus BU is equal to F, where A and B are n by n matrices, and F is a nth vector, and U is a nth vector unknown vector which is going to be find, and the corresponding matrix differential operator of a given system 2 can be represented L is equal to AD plus B, which is a matrix differential operator that is taken from KZ D n power n, n by n. Now, before going to find the reduction algorithm, we call some basic definitions of matrix differential operator. A matrix differential operator T is said to be unimodular if there exists a matrix B, n by n matrix, such that Vt is equal to Tv is equal to identity matrix. That is, there exists a matrix V which is a two-sided invertible matrix. That is, invertible means we know the determinant of T is non-zero constant. Let L is equal to AD plus B, a n by n matrix differential operator. Then rank of L is defined as a rank of coefficient matrix A. That is, rank of a given matrix differential operator is equal to rank of coefficient matrix A. Two differential operators L and L tilde are said to be equivalent if there exist two unimodular matrices S and T, such that L tilde can be written as the product of S, L and T. So these are some basic definitions, and we are going to use these definitions to find a reduction algorithm. After that, we see the map implementation. In order to develop a reduction algorithm for a differential operator L, the following theorem is one of the essential steps. So the main algorithm of the main algorithm for reduction is based on this theorem. So the theorem is as follows: let A be a n by n matrix whose entries are holomorphic power series at non-isolated point Z is equal to 0. Then there exists two unimodular matrices S and T such that SA can be written as a block matrix, where A11, in fact, SA can be written as a column block matrix. A11 as one block and 0 is another block. And AT is equal to row block matrix, that is A11 and 0. And SAT can be written as a 2 by 2 block matrix, A11, 0, 0, 0. Where A11 is R by R matrix, is a block matrix, and R being a rank of the matrix A. So this is one of the essential theorem which is applied to find a reduction algorithm. So the main theorem is as follows. There are many steps and many examples are available in the accepted paper, which is going to be coming, coming issue. So that will share you with you all. And the main content I am going to explain, because we are focusing on the implementation of this algorithm, which is accepted already by the journal. So this algorithm is verified and clear. So implementation, we are focusing on this in Maple, how to implement, because nowadays instead of applying manual calculations, applying software is important to save the time and things. So main theorem is as follows. Let L is equal to AD plus BA n by n matrix differential operator with the rank of A is equal to R, rank of B is equal to K. Then we can construct two unimodular matrices S and T such that the system of differential algebraic equations can be decomposed into two cases. The case one for R plus K is equal to n, and another case is there that will be coming next. So if R plus K is equal to n, then the given system of differential algebraic equation can be decomposed as follows. A tilde 1 1 V1 dash is equal to F tilde 1, and B tilde 2 2 V2 is equal to F tilde 2, where A tilde 1 1 is R by R matrix, and P tilde 2 2 is K by K matrix, and these two are invertible matrices. Now V can be written as a T inverse of U is equal to column matrix V1 V2, and F tilde can be written as SF, that is equal to F tilde 1 F tilde 2, where S and T are going to be calculated. That we know how to calculate by using previous theorem. And case 2 for R plus K is less than n. In that case, the system of differential algebraic equations can be decomposed as follows. A tilde 1 1 V1 dash is equal to F tilde 1, and B tilde 2 2 V3 is equal to F tilde 3, where A tilde 1 1 B tilde 2 2 are invertible matrices of order R and K respectively, and V can be written as T inverse of U, and F tilde can be written as SF, with some necessary condition on right hand side. F tilde 2 is equal to 0. What is this necessary condition? We will see with example. So that is here given. Consider the matrix differential operator L is equal to AD plus B, where L is a matrix differential is given, and in particular, if you want to find a coefficient matrices A and B, we can abstract from this L, that is A is equal to given matrix here, coefficient of D's we collected as a coefficient of differential operator A, and the remaining part will be B. So we can abstract a given coefficients A and B from given matrix differential operator as given in the slide. Now follow the main theorem. Then one can easily compute a unimodular matrices S and T, which is invertible. So after applying the main theorem, then we have calculated S and T as given here. And what are the steps involving? All this will be given in the accepted paper that will be sharing with you all if you want to go through the each steps. However, if you don't want to this, if you want to use only the particular solution of a given system of equation, then you can apply the Maple implementation. So after applying the main theorem, we will get two unimodular matrices S and T, and one can obtain the reduction algorithm L tilde is equal to S L T. And so multiplying this, then given matrix differential operator, that is here in the equation number 3, L is equal to AD plus B. This is reduced to L tilde, that is equal to, it is divided into 3 by 3 matrix. So you can see for top left corner, the block is containing only differential operator parts, and the right bottom corner containing only algebraic part, that is The given system of differential equation is divided into two parts. One is one system is containing only ordinary differential equation, system of ordinary differential equation. Another part is containing only algebraic equations. Now we can apply separately and we can get the solution of this reduced differential operator. That will be same as is solution of given differential given system of differential algebraic equations. So instead of solving this system, this solution will give the, but solving this is very simple than given system. Now we are going to focus here applying same. We are going to discuss about the same example in the map implementation. Simply we enter the coefficient matrices, then we get output. How it will be, and then we will see in the implementation. So map implementation. Now we discuss the map implementation of the reduction algorithm by creating different data types. The implementation maple package DAS, differential algebraic system reduction. The package name is given as a DAS reduction of a discussed algorithm, which is we have seen. And this algorithm is available at www.srinivasaravatota.webs.com/research. So if you are interested, we can download this reduction algorithm, you can apply. And using this maple package, one can obtain two unimodular matrices S and T, as we have seen earlier, and reduction and reduced DAS, that is differential algebraic system, that also L tilde, that is also we have seen earlier. In maple implementation, Z is a complex variable and D is equal to D over DZ is a differential operator. So in that we are going to use that implement package, that is DAS underscore reduction is the package which is available at www.srinivasaravatota.webs.com/research. And how we are going to use this package, we are going to see the simple example which we already seen. Before that, we are going to discuss about the pseudocode, and we are going to, this is the pseudocode one can see here on the slide. And we take the coefficient matrices A and B, and that will go through the step by step as given here. Total there are 17 steps, and it will go through each step, and finally we get S and T. After that, reduced differential operators, and one can these are the steps involving in reduction algorithm. And more detail, as I told you earlier, more details will be available in the accepted paper that will share with you all, that what are the steps indicating here, and if you read that paper, you will easily understand all those things. And these are the steps in the pseudocode. And sample computations, we recall the differential algebraic system given in equation, that is we have already seen one example. So consider the following matrix differential of L is equal to AD plus B, same thing, and where A and B are taken. Now we are going to use only matrices A and B only, and that will be automatically give the output, that is two unimodular matrices S and T and reduced system, that is L tilde. Directly we will get, it will go through the algorithm procedure inside maple code and then give output. So using maple implementation, DAS reduction, that is a package name of the proposed algorithm, we have A is equal to, we enter instead of Z, we use here X for simplicity in maple. So here X means, as we have a complex variable, as we have seen Z there, but here for simplicity, if you are interested, we can put Z also, no problem, but for sake of simplicity, I written X in place of Z. So A is equal to matrix, this is how to syntax for define a matrix in maple. And B is a matrix here. These two are coefficient matrices. Here we can see A and B are given. So after entering this, we can cross verify whether this A, B are matching with given A and B or not. So we can verify this. 1 minus X, 2 minus X, 1 is the first row of A. Similarly, 1 minus Z, 2 minus Z, 1 is the first row of matrix A in terms of Z, and this is in terms of X. So I have verified and all these two are matching. Now we can apply the DAS underscore reduction algorithm package. Now STL reduced. These are the outputs are going to store in S, T and L reduced names. So I'm using the package DAS underscore reduction A and B. So you are taking input here A and B matrices, and output directly will come here matrices. First matrix is showing S and second matrix is showing T, and the last one is L tilde. So one can easily also verify that using the manual calculations, applying the main theorem, we have L tilde is equal to this one. Similarly, applying proposed maple package we also have same. So here also we can observe that first block containing only system of differential equations, and the last block is containing algebraic equations only. So instead of solving given this equation, this system of equation L is equal to AD plus B, it is easy to solve the reduced system of differential equation. The solution of this will be matching with the solution of given system of differential algebraic equations. And these are some references. Thank you all. If you have any questions, you can ask me. I will be available. Thank you.
We now invite Dr. Uday Dolas, Professor, Department of Mathematics, CSA Government PG College, Sehod, Madhya Pradesh, India, to kindly present his paper. Sir, please.
My topic is fixed point theorem for semi-compatibility on complete Menger space. Next, please. My paper abstract. In this research paper, we consider fixed point of some semi-compatible map on complete Menger space. Our paper is a generalize of some known result in this field. The theory of probabilistic metric space is an important part of stochastic analysis as Stochastic interest to develop the fixed point theory in such space. There are many results in fixed point theory in probabilistic metric space. The concept of weakly compatible mapping is most general as each pair of compatible mapping is compatible, but the reverse is not true. Mr. Singh and Jain established a common fixed point theorem in Menger space using the concept of weak compatibility and compatibility of pair of self maps. We generalize the extent the result of B.D. Pant and Sunny Chauhan for 8 mapping of to 6 mapping in complete Menger space using the concept of compatibility. Next, some definition. Probability and definition. Definition number 1. A binary operation star interval O1 O1 or 01 is continuous T norm if star satisfy the following axioms conditions. Star is commutative and associative, is continuous. A star A is equal to A for all A belongs to OA. A star B smaller than equal to C star D whenever A smaller than equal to C, and B smaller than equal to D for all A, B, C, D belongs to in closed interval 0, 1. Example, T norm or A star B, AB and A star B is equal to AM and AB. Definition again, second definition, a probabilistic metric space, PM space, is an ordered pair XF consisting of a non-empty set and a function F where L, that's L is capital L, is a collection of all distribution functions, and the value of FV, the function FUV, is assumed to satisfy the following condition. What condition? Condition 1 minute. Condition, that's okay. Condition PM1FUVX is for all x is smaller than greater than 0 if and only if UV. PM2 FUV0, PM3 FUV, PM4 FUVX is equal to 1, FVWY1, then UVVX plus Y is equal to 1. Another definition, a mapping T01 you call to T norm. If TA1 is equal to A, TAB is equal to TBA, TCD is greater than equal to TAB, TABC to operate the TABTC. In definition, a Menger space is triplet. What triplet? X, F, T, where X is PM space and T is norm such that the equality. Okay, definition 2.5. The self map A and B of Menger space except T are said to be compatible if FAB, XN, BAX and T for all T is greater than 0 whenever T is sequence such that AXN, BXN is greater than T. Approx to 2.6 definition. Self-map A and S of Menger space except T are said to be weak compatible if they commutate at their consistent point, that is AP is equal to SP for some P belongs to capital N, then ASP is equal to SAP. Definition: a pair AB of self-map of Menger space except are said to be semi-compatible if AB, XN, BA, 16 is approach to 1. Whenever XN is sequence in X such that AXN, BXN is equal to X, it follows that AB is semi-compatible, AX is equal to BX, then BX. Thus, if the pair AB is semi-compatible, then it is weakly compatible, but the converge is not. Lemma 2.8, that X, F, T triplet be a Menger space if there exists some K belongs to 0, 1 such that for F, PQ, KX is greater than equal to F, PQ, then P is equal to lemma. Lemma 2, let Xn be the sequence in Menger space XFT with continuous T norm and Txx is greater than equal to X. Suppose for all X belongs to 0, 1, there exists K content 0, 1 such that for all X is greater than equal to Q. Cauchy sequence. Xn is a Cauchy sequence. That's our main result, our main theorem. What statement? Let A, B, S, T, and Q are self-mapping of a complete Menger space XFT satisfy property number 1. AX smaller than equal to STX, BX smaller than equal to PQX. Second one, PQ is equal to QP, ST is equal to TS, AQ is equal to QA, BT is equal to TB. 3. Either A is continuous or PQ is continuous. 4. APQ is semi-compatible and BST is weak compatible. There exists K belongs to 0, 1 such that infinity FAXBY KT is greater than equal to minimum FPQ STY FT F of PQ AST B PQ STT F AXPQY T. The proof of our main theorem result said that firstly we have proof Yn is a Cauchy sequence, then some cases putting x is equal to xn to n, y is equal to x to n plus 1, and similarly therefore n, our two cases n or odd even, the consistently we notation that the proof Yn is Cauchy sequence in x which is complete. Okay, and then we shall use the fact that subsequence y2n also converts to z. But the some case 1, when A is continuous, then AAXN is greater than equal to Z. And then we have PQZ is equal to AZ. Firstly, step one, putting x is equal to z, y is equal to x2n plus. Then taking the limit and az is equal to pqz is equal to z. Step 2, x is subset of stx. Then there exists again the w, and some proof point is again a, p, q, b, s, t are weakly compatible. Step 3, putting x is equal to xn and y is equal to z. Then some results, hence z is equal to bz is equal to stzd. Step 4, putting x is equal to x2n, y is equal to tz. Then some calculation, then by proof tz is equal to t, stz is equal to tz is equal to z implies sz is equal to z. Then we find sz is equal to tz is equal to bz is equal to az is equal to z. Step 5, putting x is equal to qz and y is equal to x2n plus 1, then we get result. Therefore, compatible all the results, we get az is equal to bz is equal to sz is equal to tz is equal to pz is equal to qz is equal to z. Then z is a common fixed point of mapping a, b, s, t, p, q. That is the case first. Case second, case 2, if pq is continuous, the proof follows by case 1. Uniqueness condition, let z be the another common fixed point a, b, s, t, p, q, then no problem. Again we are proved that therefore z is the common fixed point theorem, common fixed point of a, b, s, t, p and q. There is the final result. Z is the unique common fixed point of a, b, z, s, t, p. Some references there, but very main reference is Chang S, the nonlinear operator theory, probabilistic metric space, but the semi-computable and fixed point Menger space. But the third point, third reference is computable mapping and common fixed point. But main our number 6, Pant, BD and Chauhan, Sunny fixed point theorem in Menger space using semi-computable test to get. And again last one is 10th, Singh B and Jain as a fixed point theorem in Menger space to be completed. Thanks all of you.
Thank you, sir. We now invite Dr. Satya Narayana Sa, Associate Professor, Department of Mathematics, AMC College, Biratnagar, Nepal. Sir, kindly present your paper.
Respected chairperson, honorable chief guest, distinguished scholars, and participants. I am Dr. Satya Narayana Sa from Menborang Adarsh Multiple Campus, Tirvan University, Biratnagar, Nepal. Title of my paper is Characterization of Nuclear Spaces through Summability. Introduction. Theory of nuclear spaces. The theory of nuclear spaces was developed by the great mathematician of Germany, Alexander Grothendieck, in 1955. A nuclear space. A nuclear space is a topological vector space with many of the good properties of finite dimensional vector space. Co-nuclear spaces. A co-nuclear space is also a locally convex space whose strong topological dual is nuclear space. Mathematicians and researchers. There are many renowned mathematicians and researchers who made variable contribution in this field. Some of the notable mathematicians are such that A. Pitch, G. Kothe, E. H. Murray, T. Kumura, Y. Kumura, N. Brookie, K. Johan, C. Beska, and G. I. Litno. They have made significant contribution in this field. Research question. There are many open questions in the theory of nuclear locally convex space. One of which is every nuclear space co-nuclear? Objective. The main two objectives of the paper are: first, to analyze nuclear and co-nuclear spaces through solubility, and second, to identify a co-nuclear spaces. Significance of a study. The theory of nuclear space and co-nuclear spaces is one of the latest branches of mathematics, which has wide application in other branches of sciences. It is important to study this theory because it is widely used in a space mission and also applied to engineering, physics, biomedicine, and so on. Review of literature. Grothendieck established the important internal criterion such that a materializable locally convex space is nuclear if and only if every summable sequence in it is also absolutely summable. Pitch characterized nuclear spaces are those locally convex spaces for which appropriately topologized spaces of summable and absolutely summable sequences are the same algebraically. E. H. Murray gave the definition of summable families of vectors. He also showed that an infinite series of real or complex numbers converges unconditionally if and only if it is summable. T. H. Hildebrandt had been studied of families of inert space and so on. The research gap. Despite the contributions of the previous researchers, characterization of nuclear spaces through summability is still unclear. Therefore, the present study makes an attempt to fill the research gap. Method. The present study is based on the 5 main following theorem proposition of A. Pitch, such that if E is a locally convex space, then for every index set I, the relation vector space of all weakly summable class of vectors equivalent to vector space of all absolutely summable class of vectors equivalent to vector space of all summable class of vectors. Second, let E be a locally convex space if there exists an infinite index set I for which the relation vector space of all weakly summable class of vectors equal to vector space of all absolutely summable class of vectors. Second, vector space of all summable class of vectors equal to vector space of all absolutely summable class of vectors holds then E is nuclear. Third, all locally convex space E is nuclear if and only if for at least one infinite index set I, the relation vector space of weakly summable class of vectors equivalent to vector space of all absolutely summable class of vectors, or vector space of all summable class of vectors equivalent to vector space of all absolutely summable class of vectors holds. Fourth, every co-nuclear space is boundary summable if E is co-nuclear. Then vector space of all weakly summable class of vectors equal to vector space of all summable class of vectors equal to vector space of all absolutely summable class of vectors less than E holds for every index set I. 5. E is co-nuclear if and only if E is boundedly summable and vector space of weakly summable class of vectors equal to vector space of all absolutely summable class of vectors, or vector space of all summable class of vectors equal to vector space of all absolutely summable class of vectors for infinite index set. Result: or nuclear locally convex space E is co-nuclear if E is boundedly summable. At the end, on the occasion of coming Diwali and Chhath Parv, I wish you all, may this Diwali and Chhath bring you all cracker with joy, firework with happiness and prosperity. Thanks. References are given here. Worries. Thanks again.
Thank you, sir. We now invite Dr. S. Jafarunisa, lecturer in mathematics, Government College for Women, Kurnool, Andhra Pradesh, to kindly present her paper. Madam, please.
Respected dignitaries, good evening. Myself Jafar Nisa, lecturer in mathematics from GCM Kurnool. Today I am going to present the paper Effect of Hall Effects on Mixed Convective Heat and Mass Transfer Flow of a Nanofluid in a Vertical Channel with Stretching and Stationary Walls in the presence of non-uniform heat sources. The study of magnetohydrodynamics heat transfer with Hall currents has several engineering applications in power generators, transmission lines, refrigeration coils, etc. And the study of Hall effects on nanofluid has applications in magnetohydrodynamic energy generators, and study on the problem of Hall current in nanofluids over a stretching sheet is very limited. Several authors have studied the Hall effects on magnetohydrodynamics flow heat transfer of nanofluids over a stretching wedge in the presence of velocity sip and Joule heating. And using the model developed, the effect of buoyancy ratio number, Hall current parameter, etc. are studied in this paper. And the present investigation deals with the boundary layer flow, heat and mass transfer flow of a nanofluid in a vertical channel bounded by the stretching as well as the stationary walls under the influence of a non-uniform magnetic field, and similarity transformations are used to convert the governing partial differential equations into a system of non-linear ordinary differential equations, and they are solved numerically by using the Runge-Kutta method and as well as the shooting method, and the effects of different parameters will be discussed numerically through graphs and tables. And this is the formulation of the problem. Here we consider the two-dimensional convective heat and mass transfer flow of a viscous electrically conducting fluid through a porous medium. Here we will take the vertical channel. Here rectangular coordinate system is taken here, where these two walls y equals to minus L and y equals to plus L. On the left side we will take the stretching plate, and as well as at the right side we will take the stationary plate. Here a uniform magnetic field of strength H0 is applied normal to the walls. And assuming the Reynolds number to be small, here we neglect the induced magnetic field when compared to the applied magnetic field. Here these are the boundary conditions at both the walls. Here u equals to bx, that is primary velocity is bx at y equals to minus L wall, and whereas at plus L this will be 0, and the secondary velocity is 0 in both the cases. And that in case of the temperature, T1 and T2 are the temperatures at y equals to minus L and y equals to plus L respectively, and the concentrations are C1 and C2. These are the concentrations of the fluid. Here we assume that the nanofluid is isotropic and homogeneous. So here we express the velocity, temperature, concentrations in this form. Here we assume that the fluid is isotropic, homogeneous, and it has a constant viscosity and electric conductivity. And taking the viscous dissipation and Joule heating effects into consideration, these are the governing equations of the flow, heat and mass transfer flow of the nanofluid with Hall effects. Here the equations 1, 2, 3 and 4, this represents the equations of the governing flow. So here these are the boundary conditions which were discussed earlier. Here B is the stretching rate of the channel, and as usual here T1, T2 are the constant temperatures, and these are the constant concentrations of the channel walls respectively. Here we introduce the similarity variables here. So eta equals to y by L, u equals to bx, f dash, these are all the similarity variables. Here we eliminate the pressure between the equations 3 and 4, and using 1 the momentum equation will be reduced like this, where gr is a Grashof number and pr Prandtl number. A1 indicates a space dependent heat source. Here B1 indicates a temperature dependent heat source parameter. Lewis number is Le. Next, here gamma is the chemical reaction parameter, EC represents the Eckert number, that is dissipation, NR represents the radiation parameter, etc. Here the boundary conditions in non-dimensional form. After applying the similarity variables, here the problem will become in dimensional form, and in dimensional form the boundary conditions are like this: f plus r minus 1 equals to 0, f dash of minus 1 equals to 1, and so on, and we will call it as equation number 12. A usual approach is to write the nonlinear ordinary differential equations in form of first order initial value problem like this, and these are the nonlinear ordinary differential equations. They are coupled each other, and we will solve these equations by using the shooting method and Runge-Kutta method. Here f3 of minus 1 and f4 of minus 1, these are at minus 1, the values f3, f4, f6, f8, f10, these are unknown initial conditions. So we will apply the shooting methodology, and the missing initial conditions, they are coupled so that the solution satisfies the boundary conditions in dimensional form. And results and discussion. So here in this analysis we mainly investigate the influence of non-uniform heat sources on convective heat and mass transfer flow of the viscous dissipative nanofluid in a vertical channel, which is bounded by the stretching sheet and as well as the stationary plates. Here the nonlinear equations they have solved by employing the fourth order Range-Kutta method and shooting techniques. If we observe the figures here figure 2a to 2d, this represents the variation of velocities, temperature and concentration of the nanofluid with the change in the heat source parameter here m, Hall parameter m. Here we can observe that there is an increase in Hall parameter m with increase of the primary and secondary velocities. Next 3a to 3b, these represents the variation of the values of velocities, temperature and concentration with the variation of the A1, that is space dependent heat source parameter. And figures 4a to 4d represents the variations with the dependent heat source parameter D1, and 5a to 5d represents the velocities with the chemical reaction parameter. Here we can observe that the primary and secondary velocities increase in both degenerating and as well as generating chemical reaction cases. And the nanoparticle concentration increases with increase in the values of the chemical reaction parameter. And this represents the variations with the Eckert number, that is a dissipation. And here we can observe that higher the dissipative energy, smaller the concentration in the flow region. And these are the variations with the change in the radiation parameter NR. And figures 8a to 8d, this represents the effects of Brownian motion, and figure 9a to 9d represents the effect of thermophoresis parameter. And here if we observe the table 1 and table 2, these represents the variation of stress components tau x and tau z, and Nusselt number, that is rate of heat transfer, and rate of mass transfer, Sherwood number at both the walls -1 as well as the +1. Here for different values of Hall current parameter, chemical reaction, Eckert number, space dependent parameter, heat source dependent parameter, Brownian motion, thermophoresis parameter and radiation parameter, for different values how the values are changing we can observe in these tables. Now by observing all the figures and tables which are stress components, rate of heat transfer and mass transfer, the final conclusions are like this. An increase in Hall parameter m, it increases both primary as well as the secondary velocities and decrease the skin friction components. And with increase in the space dependent parameter, both the velocities enhances, and in the presence of the heat generating, that is absorbing source B1, heat is generated in the flow region which increases both the velocities. Higher the dissipative energy, larger the magnitude of the velocities. Higher the dissipation, smaller the skin friction components. Increase in the radiation parameter facilitates the enhancement of both the velocities and increase the thickness of the boundary layer. And radiation parameter enhances the values of skin friction components tau z and reduces the skin friction component tau x. And Nusselt number as well as the Sherwood number, they enhances at the wall y equals to +1. And increase in the Brownian motion enhances the primary velocity and secondary velocity. So thickness of the hydromagnetic boundary layer enlarges. Increase in chemical reaction parameter increases the velocity, temperature and nanoparticle concentration in the flow region. And increase in the chemical reaction parameter, here it enhances the skin friction component tau x, reduces tau z, Nusselt number on the wall in degenerating chemical reaction, whereas in generating case we can observe the reverse effect. And these are the few references, and thank you for.
Thank you, madam. We now invite Dr. P. Gayatri, lecturer in mathematics, Government Degree College, Raichot, Kadapa District, Andhra Pradesh, to kindly present her paper. Madam, please.
Respected dignitaries, professors, speakers, and my dear colleagues, good morning to one and all. This is Dr. P. Gayatri, lecturer in mathematics, Government Degree College, Raichoti, Kadapa District. Today I am going to present the paper, Effect of Chemical Reaction, Thermal Radiation and Radiation Absorption on convective heat and mass transfer flow of a Jeffrey fluid in a concentric cylindrical annulus with non-linear density temperature revelation in the presence of constant heat source. First, we discuss the Jeffrey fluid. Jeffrey fluid model is capable of describing the stress relaxation property of non-Newtonian fluids, which the usual viscous fluid model cannot describe. Next, we go to abstract. The effect of non-linear density temperature, variation of mixed convective heat and mass transfer, flow of a Jeffrey fluid through a porous medium in a circular annulus in the presence of constant heat sources is considered. The equations governing the flow, heat and mass transfer have been solved by employing Gauss-Seidel iteration procedure. The effect of various governing parameters on the flow characteristic have been discussed graphically. The rate of heat and mass transfer are evaluated numerically for different variations. Next, we discuss the introduction. A large class of real fluid does not exhibit in the linear relationship between stress and the rate of strain. Because of the non-linear dependence, the analysis of the behavior of the fluid motion of the non-Newtonian fluids tends to be much more complicated and subtle in comparison with that of the Newtonian fluids. These are the equation. Next, the formulation of the problem. We analyze the fully developed steady laminar free convective flow of a viscous electrically conducting Jeffrey fluid through a porous medium confined in an annular region between two vertical coaxial porous circular pipes in the presence of heat generating sources. We choose the cylindrical polar coordinate system r theta z with the inner and outer cylinders at r is equal to a and r is equal to b respectively. The fluid is subjected to the influence of a radial magnetic field h0 by r. Pipes being sufficiently long, all the physical quantities are independent of the axial coordinate z. The fluid is chosen to be of small conductivity so that the magnetic Reynolds number is much smaller than unity and hence the induced magnetic field is negligible compared to the applied radial field. Also, motion being rotationally symmetric, the azimuthal velocity v is 0. These are the equations. The equation governing free convective heat and mass transfer flow under pressure gradient are the equation 1, 2, 3 are the equations. Next, equation 4 is the non-dimensional variables. We use the non-dimensional variables we get the equations, equation 5, 6 and 7. These are the Hartmann number, Grashof number. We get suction parameter, Darcy parameter, Prandtl number, heat source parameter, non-linear density temperature, radiation absorption parameter, chemical reaction, density ratio, width of annular region. Next, shear stress on Nazar number and Sherwood number. The shear stress on the pipe is given by tau dash is equal to mu of dou W by dou R is equal to A comma B. Next, the result and discussion. The equations governing the flow, heat and mass transfer have been solved by numerical technique. The velocity, temperature and concentral distributions have been discussed graphically for different parametric variations. We flow the convection that the non-dimensional temperature concentration is positive or negative according as actual wall temperature concentration is greater or lesser than the ambient temperature concentration. The non-dimensional temperature convection is positive or negative according as the actual temperature T is greater or lesser than equilibrium temperature TE. The non-dimensional temperature concentration is positive or negative according as the actual concentration is greater or lesser than the equilibrium concentration C infinity. Figures 2 to 10 represent the axial velocity W, the non-dimensional temperature distribution theta, the non-dimensional concentration C for different values. These are the graphs. Figure 2a represents variation of W with N. 2a represents W with buoyancy ratio N. It can be seen from the velocity profiles that when the molecular buoyancy force dominates over the thermal buoyancy force, the magnitude of the axial velocity enhances in the entire flow region and the region of reversal flow grows in size. Figure 2b represents variation of theta with buoyancy ratio, and it can be seen from the profiles that the actual temperature reduces in the region 1, 1.5 and enhances in the region 1.5, 2.0, irrespective of the directions of the buoyancy forces. These are some figures. Variation of W with alpha. Figure 3b is variation of theta with alpha. These are some graphs. Variation of W. Figure 5a variation of W with gamma. Figure 5b represents variation of theta with gamma. Figure 5c represents variation of C with gamma. These are some graphs. Figure variation of W with Q1. Higher radiation absorption parameter Q1, larger the actual temperature in the entire flow region 1.0, 2.0, figure 7b represents. This is the effect of Jeffrey parameter lambda 1 on W can be seen from figure 8a. It is found that modulus of W experience a depreciation in the region 1, 1.5, an enhancement in the region 1.5, 2, and the region of reversal flow increases with lambda 1 in the entire flow region. These are some graphs. Next we discuss the shear stress. Table 1 represents shear stress. Next table 2 represents the Nusselt number. The shear stress Nusselt number and Sherwood number at the inner and outer cylinders R is equal to 1 and R is equal to 2 are shown the tables 1, 2 for different parametric variations. These are the conclusions. An increase in suction parameter lambda enhances the velocity and temperature. The axial velocity W and the temperature depreciates, the concentration reduces in the degenerating chemical reaction case and enhances in the generating chemical reaction case. Higher the radiation absorption parameter Q1, modulus of W and theta in the flow region. An increase in Q1 enhances modulus of tau and reduces Nu at both the cylinders. Modulus of W and theta experiences an enhancement with increasing Jeffrey parameter lambda 1, whereas it leads to a depreciation in the actual concentration. Higher the suction parameter lambda, smaller modulus of W and larger the temperature in the flow region. An increase in the density ratio gamma 1 result in an enhancement at R is equal to 1 and 2, where as it reduces modulus of Nu, modulus of HR reduces at R is equal to 1 and enhances at R equal to 2. An increase in lambda 1 enhances modulus of tau and reduces modulus of Nu at modulus of Hs at R is equal to 1, while they enhance at R is equal to 2. These are the some references. Thank you. Thank you for giving me this opportunity.
Thank you, madam. We now invite Miss S. Anita Ruth, PhD Scholar, Department of Mathematics, St. Mary's College Autonomous, Tuticorin, Tamil Nadu, India, to kindly present her paper. Madam, please.
Good morning. I am Mrs. Anita Ruth, PhD Research Scholar, St. Mary's College, Tuticorin. Under the guidance of Dr. P. Ambrosio, Assistant Professor of Mathematics, St. Mary's College, Tuticorin. My topic is alpha A star generalized closed set in topological spaces. The definition is the subset A of a topological space F is said to be alpha A star generalized closed if alpha star closure of A contained in U, whenever A contained in U and U is open in X, tau, the class of all alpha A star generalized closed sets in topological spaces F is denoted by alpha A star generalized C of X. Here is the example. The theorem. Every closed set in F is alpha A star G closed. The converse of the above theorem will not be true. Here is the example. Theorem. Every alpha closed set in F is alpha A star generalized closed. The converse of the above theorem need not be true. Here is the example. Every alpha G closed set is alpha A star generalized closed. The converse of the above theorem need not be true. Here is the example. The theorem, every alpha A star generalized closed set is G alpha closed. The converse of the above theorem need not be true. Here is the example. From the above observation, we have closed. Every closed set is alpha A star generalized closed, and every alpha A star generalized closed is G alpha closed. Therefore, alpha A star G closed lies between closed set and G alpha closed. Here it is explained clearly in the graphical representation. The concept of alpha A star generalized closeness and semi-star closeness are independent. The concept of alpha A star generalized closeness and semi-closeness are independent. The concept of alpha A star generalized closeness and pre-closeness are independent. The concept of alpha A star generalized closeness and G closeness are independent. Here is the figure. The remark, union of two alphas A star G closed set need not be alpha A star generalized closed. The intersection of two alpha A star generalized open sets need not be alpha A star generalized open. So these are the references. Finally, alpha A star generalized closed set in topological spaces. Thank you.
Thank you, madam. We now invite Sister I. Sahayadani, Research Scholar, Department of Mathematics and Mary's College Autonomous, Tuticorin, Tamil Nadu, India, to kindly present her paper. Sister, please.
Good morning to all, and I am very grateful to the organizing team for granting me this great chance to present my paper. I am going to present a paper titled Alpha Star AS Homeomorphism in Topological Space. I am Sister Sahayadani, a research scholar from St. Mary's College, Thuthukudi, and I am very grateful to my guide, Dr. P. Anbarasi Rodrigo. Here is the abstract of my paper. Levine introduced the concept of generalized closed set of a topological space. Alpha star AS closed set is introduced by Sahayadani and P. Anbarasi Rodrigo in topological spaces. In this paper, we introduce alpha star AS closed maps and alpha star AS open maps in topological spaces. And also we introduce alpha star AS homeomorphism and study some of their characterization. First, we see the definition of alpha star A is closed maps. Let x and y be the topological spaces, then a function f from x to y is said to be alpha star A is closed function if the image of every closed set in x is alpha star A is closed in y. Here is an example for the alpha star A is closed function. We have a theorem based on this definition. A function f from x to y is alpha star A is closed function if and only if alpha star A is closure of f of A is a subset of f of closure of A for every subset A of x. Let f from x to y be alpha star A is closed function, and A is a subset of x. Closure of A is closed in x, and hence closure of f of A is alpha star A is closed function in y. Closure of A is always a subset of A. It implies that closure of f of A is a subset of f of A. So if alpha star A is closure of f of closure of A is the alpha star A is closed set containing f of A. It follows that alpha star A is closure of f of A is a subset of alpha star A is closure of f of closure of A, which is nothing but f of closure of A. Conversely, let A be any closed set in X. Closure of A is equal to A, and so f of A is equal to f of closure of A, which contains alpha star A is closure of f of A by the given hypothesis. Also, it follows that f of A is a subset of alpha star A is closure of f of A. Hence, f of A is nothing but alpha star A is closure of f of A. That is, f of A is a closed alpha star A is closed, and hence the function is alpha star A is closed function. The next theorem is function f from x to y is alpha star A is closed if and only for each subset S of y and for each open set A of x containing f inverse of S. There is a alpha star A is open set B of y such that S is a subset of B and f inverse of B is a subset of A. Let S be the subset of y and A be a open set of x such that f inverse of S is a subset of A. Now, y difference f of x difference A, say B is alpha star A is open set containing S and y such that f inverse of B is a subset of A. Conversely, let f be a closed set of x, f inverse of y difference f of f, and x difference f is open. Now, there is a alpha star A is open set B of y such that y difference f of f is a subset of B, and f inverse of B is a subset of x difference f. Hence, f is a subset of f x difference f inverse of B, and thus y difference B is a subset of f is a subset of f of x difference f inverse of B is a subset of y difference B, which implies f of f is nothing but y difference B. Since y difference B is alpha star A is closed, f of f difference B is alpha star A is closed set in y for every closed set f in x. Hence, f is a function from x to y is alpha star A is closed function. And we have the composition of two alpha star A is closed function need not always be alpha star A is closed function. This is proved by this example. And then we have a definition. Function f from x to y is said to be alpha star A is open function if the image of f of A is alpha star A is open in x for each open set in y. And we have a theorem. Let the function f from x to y is alpha star A is open function if and only if f of interior of A is a subset of alpha star A is interior of f of A for each subset of A of x. This is also like a closed function theorem. Suppose that f from x to y is B alpha star A is open function, then A is a subset of x, then interior of A is open in x, interior of A is a subset of A, so f of interior of A is a subset of f of A, thus f of interior of A is a alpha star A is open contained in f of A, hence f of interior of A is a subset of alpha star A is interior of f of A. Conversely, let we take f of interior of A is a subset of alpha star A is interior of A for every subset A of x. Let f be an open set in x, then f interior of f is nothing but f. F of f is a subset of f of interior of f is a subset of alpha star A is interior of f is a subset of is equal to f of f. Hence, f of f is nothing but alpha star A is interior of f of f. Hence, f of f is alpha star A is open in y for every open set f in x. Hence, f is a function from x to y is a alpha star A is open function. And we have a main definition here. Alpha star A is homeomorphism. A function f from x to y is said to be alpha star A is homeomorphism if f is 1 to 1 and on to f is alpha star A is continuous and f is alpha star A is open. Here we have a important theorem. Let f from x to y be a 1 to 1 and on to mapping if f is alpha star A is homeomorphism. F is alpha star A is homeomorphism if and only if it is closed and continuous. We take f as alpha star A is homeomorphism first, then it is alpha star A is continuous, and then we have a arbitrary closed set x. We take a closed set x, then A difference x is open. F is alpha star A is open. F of A difference x is alpha star A is open in y. That is f of difference f of A is alpha star A is open in y. So f of A is alpha star A is closed in y. So it is closed. The function is closed. Conversely, let f be alpha star A is closed set and alpha star A is continuous. Then G, we take G as a open set in x. X difference G is closed. F is alpha star A is closed. F of x difference G is alpha star A is closed up into the F of x difference G is closed in y. Hence, f of G is alpha star A is open in y for every open set G in x. Thus, f is alpha star A is open, and hence this function is alpha star A is homeomorphism. Then we have a theorem. Let f is a function from x to y is a homeomorphism, then it is alpha star A is homeomorphism, but not conversely. Obviously, if we take a function as a homomorphism, it is bijective, continuous, and open. Hence, f is a function from x to y is alpha star A is continuous. Since f from x to y is open, the image of every open set in x is open in y, so it is alpha star A is open, and every open set alpha star A, so every open set is alpha star A is open, and hence f from x to y is alpha star A is open. Therefore, every homeomorphism is alpha star A is homeomorphism. The converse is not true. That is explained proved by a example. And then we have a theorem. If a function f from x to y is a homomorphism, then f is every alpha homeomorphism is alpha star A is homeomorphism. Every R homeomorphism is alpha star A is homeomorphism. Every G homeomorphism is alpha star A is homeomorphism. Every alpha G homeomorphism is alpha star A is homeomorphism. And every G alpha homeomorphism is alpha star A is homeomorphism. Here we define a function which is alpha A homeomorphism. Then it is obviously alpha continuous and alpha open. We know that every alpha continuous is alpha star A is continuous, and every alpha open is alpha star A is open, and hence this is alpha star A is homeomorphism. This proof is true for all the statements, but the converse of these statements are not true. That is given by these examples. And we have a theorem. Let x f from x to y be alpha star A is continuous function. Then the following are equivalent. Alpha star A is open function implies alpha star A is homeomorphism. Alpha star A is homeomorphism implies alpha star A is closed function. Alpha star A is closed function implies alpha star A is open function. First we prove the first part. One implies true. By the given hypothesis, being it is open function, this is a bijective function, and it is a continuous function, hence it is a homeomorphism. The second part, it's 2 implies 3, that is we take a function as a homeomorphism, so it is alpha, obviously alpha star A is open, and we take a closed set A in x, A complement is open, f of A complement is open in y, f of A complement is nothing but f of A the whole complement is open in y, so f of A is closed in alpha star A is closed in y, so for every closed set A in x, so this f is a closed function. Then third part, the 3 implies 1. Let f be a open set in x, f complement is closed. Again, f of f complement is nothing but f of f the whole complement, which is closed. So f of f is open in y for every open set f in x. Therefore, the function is alpha star A is open function. And we have the final result is the composition of 2 alpha star A is homeomorphism need not always be alpha star A is homeomorphism. Here we take 3 topological spaces and we define 3 topology and we define 2 functions. These 2 functions are alpha star A is homeomorphism, but their composition function G composite F is not a alpha star A is homeomorphism because the alpha star A is continuous condition while X. Thus, the composition of 2 alpha star A is homeomorphism need not always be alpha star A is homeomorphism. Here are some references that is used in this paper. Thank you for all. Thank you once again for the organizing team and for all the participants. Thank you.
Thank you, sister. We now invite Ms. Mamata Mahavir Kuti, Research Scholar, Department of Mathematics, Rani Chennamma University, Belgavi, Karnataka, to kindly present her paper. Madam, please.
Namaste everyone. I am Mamta Kutte, research scholar from Rani Chennamma University, Department of Mathematics, working under the guidance of Professor T. Venkatesh. He is going to present a paper titled A Note on the Cattle Problem. So, in this paper, we have made an attempt to see how the Diophantine problems in its model terminology, it connects to and have its impacts on the number theory and related problems for geometry as well as analysis. So in the first section, that is introduction, I'm going to tell a little bit about the Diophantine equation, its history, its background. So Diophantine equation dates back to the Greek days. Around the 3rd century BC, Diophantus of Alexandria was interested in solving such equations, and he wanted to find the solution of such equations only in the integers. Then gradually, after certain number of years, its scope also spread, and then the major turn that this study took was Batchett's translated work, and then the imagination of format around 1640s, later Euler and Lagrange's in 17th and 18th century respectively. So the classical example of the Diophantine equation due to Fermat, it is x to the power n plus y to the power n is equal to z to the power n. For a higher exponent n, that is n greater than 2, it does not exhibit any non-trivial integer solution. And to prove this, it took almost 350 years. So Andrew Wiles in the year 1993 came up with the proof of the conjecture, and thereby settling this problem. This equation also paved for many interesting themes in the number theory and arithmetic geometry. And the Cattle problem, it is the variant of form of the Diophantine equation, that is x to the power n plus y to the power n is equal to z to the power n. And it has interesting origin, and attempts to solve the problems provided new twist to the arithmetic nature of the problems, the nature of the numbers. I have given two references. So in order to ascertain this interesting analogy, we in a way look at the very structure of the number line, that is R. So we have dealt here in this paper with the Pell's equation, and we have also made a note on the continued fractions, and these continued fractions will help us to solve the Diophantine equations. So here, if we take the equation which is of the form x square is equal to dy square plus 1, where d is any square free integer, and such type of equation, it is called as the Pell equation. Actually, Pell did not do anything about this, but Euler attributed the Pell's name to it, and the name was stuck. So if I take the small value of d as 2, we get the equation, the same equation as x square is equal to 2y square plus 1. So when we look at this equation, clearly when we try to solve it, we come to know that 3 plus or minus 2, these are the solutions to this equation. That is, in other words, I can also put it as for what y value, what should be value of y, so that 2y square plus 1 is always a square. And from number theory, we know that every square, it is always congruent to either 0 or 1 mod 4. So therefore, 2y square plus 1 is equal to 9 is congruent to 1 mod 4, or 2y square plus 1 is congruent to 0 mod 4. Now, since y square is congruent to 0 or 1 mod 4, and 2y square plus 1 is congruent to 0 mod 4 is ruled out, and then we state the proposition, and the proposition is the equation x square is equal to 2y square plus 1, it admits the integer solution for 2y square plus 1 congruent to 1 mod 4. Now for the same equation, 3, 2 as well as 17, 12 are also the solutions. Now if we take equation as x square equal to 3y square plus 1, then it admits the integer solutions 2, 1 as well as 7, 4. Now any equation x square plus dy square equal to 1, where d is a square free integer, it admits infinite solutions. And since this is because 3y square plus 1 is congruent to 0 or 1 mod 4, which will admit integer solutions in this case. So in general, we can expect infinite number of solutions to such types of equation, that is x square is equal to, in general, dy square plus 1. Now, in the second section, we are talking a little bit about units in the rings. So we know that if we take the set Z plus, then it has got only two units, that is plus 1 and minus 1. So when we solve equations for the integer solutions, for this, if we consider the Pell equation, that is x square equal to dy square plus 1, where d is square free integer, that is x square, same equation we can write it as x square minus dy square equal to 1. So when we factorize, we get it as x minus root d into y in first bracket, and the second bracket x plus root dy is equal to 1. Now suppose if u is unit of the ring, u belongs to R, which is a unit in the ring, then there exists v in R such that u into v, product of it must be equal to 1, and then v will be equal to 1 by u. So in case of when we take a set of integers, it has got only two units, that is plus and minus 1. So whenever a ring is given, to determine all its units, it is a non-trivial problem. So from the above observation, we find that the units hold a very important key to solve the dependent problems, and therefore the Pell equation and its solutions can be seen for the rational fields which are extensions of the set of rational, that is Q, and this Q is subfield of the set of complex number C. So further, the line of this investigation has enlarged the scope of solving Diophantine equations from integer solutions to the rational solutions and then the number fields. So in the next section, we will be talking about continued fractions. So in this section, we will give an interesting characterization of the continued fractions. So every rational and irrational as well as also a whole number can be viewed as a continued fraction. So I have given here a definition of the continued fractions. So if we are able to express any real number in this staircase notation, we call it as continued fractions. So I have expressed here, I have given two examples wherein we have expressed this improper fraction 37 by 11 as a continued fractions, as well this root 2 also we can express it as a continued fractions. Now the next part, what this Pell equation is doing with Q root D. So by definition of the number field, which is extension of the Q, if we consider the simple equation irreducible over Q, that is x square minus 2 equal to 0, then when we factorize, we get x plus root 2 into x minus root 2 equal to 0. Now suppose if I take x square minus 2y square equal to 1, when we split, we get it as x plus root 2y into x minus root 2y is equal to 1. Now these two belongs to Q root 2 and these are conjugates of each other and therefore these are the units. The next part, we are talking about the polynomial ring in the two variables f of xy. So which can be mapped to two polynomials in one variable, namely x for fx and y for gy. And then continued fractions which are associated with the Pell's equations, that is x square minus dy square equal to 1. It has some far-reaching consequence on the real line, that is r. And then every real number, if I take it as alpha which is belonging to r, then in the limiting sequence of the rationals, as this alpha minus pn upon qn tends to 0, as n tends to infinity. So when this satisfies this condition, we call that alpha is well approximated through this limiting process, and the other extreme is this can be also badly approximable. So badly approximable numbers have some connections with the dynamics underlying space, which is also associated with the stability of the system or fixed points of the invariant. And then the last part, we are talking about group actions and modular surfaces. So group action definition I have given, and then this group action G on X, when it is quotiented over G, we get the quotient space. And when we take R quotiented over Z, which is equal to S, is a one-dimensional closed oriented smooth manifold, and H quotiented over special group 2Z, which is two-dimensional modular surface. So in order to modular group H quotiented over SL2Z, we perform the simple quotient operation on C, choosing a lattice. So given in this case L equal to M omega plus N omega 2, where omega 1, omega 2, Mn belongs to Z. So translation of on the account of the group action can be attributed to the geodesic flow and the modular surfaces, and this was convinced as a problem in 3 stages, which we have discussed elsewhere in our work. So I've given here few references. So I stop here. Thank you.
Thank you, madam. We now invite Sister I. Sahayadani, Research Scholar, Department of Mathematics, St. Mary's College, Autonomous, Thoothukudi, Tamil Nadu, India, to kindly present her paper. Sister, please.
Sahayadani, a research scholar from St. Mary's College. I'm very grateful towards the organizing team for granting me this grand chance of presenting my paper. I am presenting a paper titled Control First Order AS Continuous Functions in Topological Spaces. I am very grateful towards my guide, Dr. Pian Parasi Rodrigo. And here is my abstract. The purpose of this study is to introduce a new class of control continuous function. that is called contra alpha star A is continuous function. And also we study contra alpha star A is irresolute function. The definition of contra alpha star A is continuous function is let x and y be two topological spaces. A function f from x to y is called contra alpha star A is continuous if the inverse image of every open set in y is alpha star A is closed to set in x. An example is given for this contra alpha star A is continuous function. Let x and y be two topological spaces. Let x from y, f from x to y, then f is the contra alpha star A is continuous function if and only if its inverse image of every closed set in y is alpha star A is open set in x. We define a function and we take S as a closed set in y. F is contra alpha star A is continuous function. So f inverse of y difference is which is nothing but x difference f inverse of s is alpha star A is closed set in x. Hence f inverse of s is alpha star A is open set in y. So conversely, let S be an open set in y. By assumption, f inverse of y difference is alpha star A is open set. Then f difference of y difference s, which is nothing but x difference f inverse of s, is alpha star A is closed set in x. Then f is contra alpha star A is continuous function. Every contra continuous function is contra alpha star A is continuous function. Let we define a map from x to y be a contra continuous function. Let S be open set in y, and we know that f is contra continuous function. So f inverse of s is closed set in x, and every closed set is alpha star A is closed set. So f inverse of s here it is alpha star A is closed set in x. Then hence f is contra alpha star A is continuous function. The converse of the above theorem need not be true. That is, every contra alpha star A is continuous function need not be contra continuous function. For that, we give an example. Every contra alpha continuous function is contra alpha star A is continuous function. For that, we define a contra alpha continuous function and S be an open set in y. Since it is a contra alpha continuous function, the inverse image of S under the map F is alpha closed set in x. Since every alpha closed set is alpha star A is closed set, F inverse of S is alpha star A is closed set in x. Hence, F is contra alpha star A is continuous function. The converse of the above theorem need not be true. That is, every contra alpha star A is continuous function need not be contra alpha continuous function. That we give prove with an example. Let x and y be any two topological spaces. F from x to y be a contra continuous function. It is alpha star A is contra continuous function if and only if it is contra G continuous function. And we first let us assume that it is a contra G continuous function. Then S be an open if S be an open set, then F inverse of S is closed set in x. Then this is a G closed set. If and only if it is alpha star A is closed. Hence F inverse of S is alpha star A is closed set in x. Hence F is contra alpha star A is continuous function. Conversely, we assume F is contra alpha star continuous function. Then S for any open set S, we have F inverse of S is alpha star A is closed set in x. S is alpha star A is closed set. Yes, it is alpha star A is closed set if and only if it is G closed. So F inverse of S is G closed set in x. Therefore, contra G continuous function. Then every contra G alpha continuous function is contra alpha star A is continuous function. Here also we define a function that is a contra G alpha continuous function. Then for the open set S, there is a closed set G alpha closed set. The inverse image is G alpha closed set. Hence every G alpha closed set is alpha star A is closed set. F inverse of S is alpha star A is closed set in x. Hence F is contra alpha star A is continuous function. The converse of the above theorem need not be true. That we prove with an example. Then let x and y be to any two topological spaces. Let f is a function from x to y be a contra alpha G continuous function. F is alpha contra alpha G continuous if and only if it is contra alpha star A is continuous function. We define a map that is alpha G continuous. Then for open set S, F inverse of S is alpha G closed set in x. So since every alpha G closed set is alpha G closed if and only if it is alpha star A is closed. hence F inverse of S is alpha star A is closed with it. Therefore, F is contra alpha star continuous function. Conversely, if we assume F is contra alpha star A is continuous function, then there exists a open set S. The inverse image of this open set is alpha star A is closed set in X. Then set is alpha G closed set if and only if it is alpha G star A is closed set. Therefore, F inverse of S is alpha G closed set. Therefore, F is contra alpha G continuous function. Every contra G star continuous function is contra alpha star A is continuous function. Again, we define a map. It is contra G star continuous function. Then we take an open set S and Y. The inverse image of this F inverse of S is closed G star closed in X. Since every G star closed set is alpha G star A is closed, F inverse of S is alpha star A is closed set in X. Hence, F is contra alpha star A is continuous function. The converse of the above theorem need not be true. It is proved by this following example. The composition of two contra alpha star A is continuous function need not always be a contra alpha star A is continuous function. That is proved by this example. Contra alpha star A is continuous and alpha star A is continuous or independent. That is proved with two examples. In the first example, we take two topological spaces and we define two topologies and we define a map and we say that this is a contra alpha star A is this is a alpha star A is continuous function but not a contra alpha star A is continuous function. In the second example, we define two topologies and topological spaces and we define two topologies. We define a map and we say that this is a contra alpha star A is continuous function but not a alpha star A is continuous. Then contra alpha star A is irresolute function definition. Let X and Y be two topological spaces. A function f from X to Y is called contra alpha star A is irresolute. The inverse image of every alpha star A is closed set in Y is alpha star A is closed set in X. For that, we give one example. In topological spaces, the composition of two contra alpha star irresolute functions is always a contra alpha star A is irresolute function. This we prove. We define two maps from X to Y and G from Y to Z, and we define a composite map G composite F from X to Z is a contra alpha star A is irresolute function. Since G is a contra alpha star A is irresolute function, by definition, alpha star A is for every alpha star A is closed set S of Z. G inverse of S is a alpha star A is closed set in Y. Since F is alpha star A is irresolute, F inverse of G inverse of S is alpha star A is closed set in X. Hence, G composite F is always a contra alpha star A is irresolute. In a topological space, the composition of two contra alpha star irresolute function is alpha star A is irresolute function. For this also we define two maps F from X to Y and G from Y to Z. We define a composite map G composite F from X to Z is a alpha star A is irresolute function. Let S be alpha star A is open set in Z. G inverse of S is alpha star A is closed set in Y. Since G is contra alpha star A is irresolute function, since F is also contra alpha star A is irresolute function, F inverse of G inverse of S is always alpha star A is closed set in X. And so G composite F is also is a alpha star A is irresolute function. Every contra alpha star A is irresolute function is contra alpha star A is continuous function. For this, we define a map F from X to Y, which is contra alpha star A is irresolute function. So S be a closed set in Y, then S is a alpha star A is closed set in Y. Since every closed set is alpha star A is closed set, hence F inverse of S is alpha star A is open in X. Hence F is contra alpha star A is continuous function. Every contra alpha star A is continuous function need not be contra alpha star A is irresolute function. That is shown in the following example. And here are some references that I used in this paper. Finally, thank you one and all. I thank you for all the organizing team once again, and thank you for all the participants for patient listening.
Thank you, sister. We now invite Dr. Vishal Kumar Sharma, Assistant Professor, Soban Singh Jeena Campus, Almora, Common University, Nainital, Uttarakhand, India, to kindly present his paper. Sir, kindly please.
Hello to all. I am just going to deliver my talk. First of all, myself, Dr. V.C. Sharma, Department of Physics, Kumar University, SSG Campus of Mohla. So I am just going to present my talk, which is on the topic existence of dark matter in high dimensional division algebra. So if you just you can just see here, I'm just going to the what are the outlines of my talk. So discuss it. This is introduction, supersymmetry, octonic electroweak formulation, octonic formulation of grand unified theory, octonic dark matter, octonic hot and cold dark matter. Then we have the result and discussion. So first of all, you can just see here. These are the outlines as I have mentioned it. So first of all, we have the introduction. Introduction means we are just going to discuss here. So, according to celebrated Hori theorem, there exists a set of the four division algebra: real, complex, quaternion, octonion, namely the real number, which are represented by R, C, H, and O. All the four divisional alternative with total antisymmetric associated. Real number explains well the Classical Newtonian mechanics, while the complex number plays an important role for the explanation beyond the framework of the quantum theory and relativity. Real and complex number are limited only to two dimensions, as you know, the x and y. So these are the, you can just say, while quaternions are extended to four dimensions. Why? That's why these named the quaternions. So one real and the three imaginary. On the other hand, octonions represent eight dimensions, one real and the seven imaginary. They have the certain properties. As you know, that real and complex number are commutative and associative, while the quaternions are associative but not the commutative, while the octonions are neither commutative and nor associative, but they have the property of alternative here. So you can just see here, quaternions are well connected to the familiar SU2 group and naturally unify electromagnetism and weak forces responsible for the electroweak SU2 cross U1 of sector of the standard model. So you can just see octonion plays an important role in the context of various physical problems like higher dimensional supersymmetry, supergravity, and superstrings here. Octonion are also useful for the unification program for strong interactions, which successful gauge theory of fundamental interactions. A theoretical description of the leptons and the quark structure of the hadrons has already pointed by the Gunadian and Gucci in the context of octonic quantum mechanics in terms of the octonic Hilbert space. Keeping in mind, in the theoretical physics, we have made analyze the role of the octonions in various unified field theories associated with the dions and dark matter here. Starting with the split octonion algebra, its properties, we have discussed the octonic unified formulation for SU2 cross U1 electroweak theory, and for this you can just see here, and SU3 cross SU2 cross U1 grand unified theory we have discussed here. So this is the introduction, and now here describing the eight-dimensional space as the combination of the two quaternion space. We have the division, the octonic space in the two quaternion space, one namely EM space and G space, and we have the unified picture of EM-G space in terms of octonic split formulation in the consistent manner. Now we have also obtained the various field equation for unified gravity electromagnetic interactions, and we have also reconstructed the field equation for the hot and cold dark matter in terms of the split octonions, and it has shown that the difference between the octonic cold and hot dark matter is significant in the formulation of the structure and of these two, because the velocity of the octonic hot dark matter cause it to wipe out the structure on the small scale here. So we have the split octonion. Now we come to the topic split octonion. Split octonion, we have the real combination of the unit octonic elements, and these are represented by O1, O2, O3, O4, O, and so on 7, and they are represented by this equation 1. Here you just see here EA are the imaginary octonic units and E0 is the real octonic unit with their properties which are given by equation 2 here. So, and further we have the structure constant which have the value +1 for these combinations represented by equation 3 here, and further we have the relation among octonic basic elements which are in terms of the Kronecker delta symbol are represented by equation 4 here. So split octonions, and this is also you can just say non-associative extension of the split octonions, and split we have the signature of the 4 by 4, whereas the octonions have positive signature 80. So these are the represented the split octonions with the basis elements by given by this equation 5 here. And This is also certain some multiplication rules are to be followed in terms of the split octonions, and they have the represented by this equation 6 here. So this is the split octonion. Now we come to the octonic electroweak formulation. As we have earlier electroweak gauge formulation, it is U1 cross SU2 in terms of the split octonion representation, where you just see here A mu, B mu are the electric and magnetic charges explained in terms of the quaternions are here represented by equation 7 here, and these are A0 mu and B0 mu are described as the electric and magnetic core potential of the ions for U1 formulations here. So this is here represented here. Octonic electroweak formulation, which is D mu, we have the double fold degeneracy of SU1 cross SU2 gauge theory is defined. This is by equation 8 here, where you just see here E and G represent the electric and magnetic charges of ions we have represented here, and which is U1 cross SU2 octonic gauge field strength of the ions in terms of 2 cross 2 John matrix realizations. And in the compact form, we have equation represented by this equation 10 here. You can just see here, this is represented, and where G mu nu, what is it? It is G are describing the non-abelian and abelian U1 cross SU2 electroweak gauge structure in the presence of the electric charge here. So this is the representation, and this is equation 12, which is representing the electroweak gauge structure due to the presence of the magnetic monopole, because it is combining the terms of B here. A corresponds to the electric one. So we have this operating d mu on this equation 24 gauge octonic gauge field strength. We get this equation 30 here. So which may be in the compact notation of the split octonion can be represented by equation 14, and this value on operating on G mu, this comes to be J nu. What is J nu? It is the U1 cross SU2 form of octonic gauge current familiar to the normal V current of the diodes. So which is the analogous continuity equation then changes to d mu J mu is equals to 0. Hence the split octonion formation of electroweak gauge theory is consistent, and the compact manner it is represented in here equation 15 here. So now we just come to the octonic formation of grand unified theory. Now the role of the octonic in the grand unified theory. Let us start with the local. We can SU3 cross SU2 cross U1 gauge symmetry, which is in the internal symmetry represented in the standard model here. The smallest Lie group which contains the standard model and upon which the first grand unified theory was based is SU5, SU3 cross SU2 cross U1, where SU2 cross U1 is the electroweak gauge theory, and when we have the gauge theory, grand unified theory, SU3 cross SU2 cross U1 in terms of the split octonion formulations. Now we have the equation 16, which is the gauge field for the generalized field of the diodes, which is we have represented here. Now we have where the components which are corresponding to the four potential of the diodes, and we just see here A mu A, B mu A, A mu alpha, B mu alpha are the SU2 and SU3 gauge field strength of the diodes in terms of the split octonion. So the covariant derivative of the SU3 cross SU2 cross U1 gauge field in terms of the 2 cross 2 John vectors matrix realization of the split octonion is described by this equation d mu. This is equals to equation this is described by equation 17 here. Equation 18, which is further this property of d mu d nu, this is represented here, where you just see here G mu Ge alpha are SU3 cross SU in the presence of elliptic, and we have this G mu 0 mu nu, this are the SU3 cross SU2 cross U1 grand unified field strength in the presence of the magnetic moment. Equation taking the form of this equation taking the form of the gauge field strength of the diodes. So we have this equation which is corresponding to the now we have octonic formation of grand unified theory. We have this equation which is representing the which may further be reduced in the compact and consistent manner in this equation, which is equation 21, which is corresponding to J mu J alpha mu nu, which is corresponding to the gauge current for the ions, which may be expressed in terms of 2 cross 2 John vector matrix stabilization. J alpha nu, which is representing the gauge current for the ions. As such, the octonic formulation regardless the generalization of the GUT for the mixing of the gauge current used for U1, SU2 and SU3 sectors associated respectively with the electromagnetic, weak and strong interaction in the presence of the ions also shows the duality invariance as well as continuity equations for the duality invariance, which is leading to the conservation of the Northern current, which is represented by equation 23. Now we come to the dark matter. Dark matter, you can just say it is a matter, habitable matter, which is accounting for the large part of the total mass in the universe. Only we have 4.6 of the total mass energy of the universe is ordinary, while 23% is thought to be composed of the dark matter. Remaining 72% is the consisting dark energy. Now it is also an even stranger component distributed almost uniformly in space and with energy density non-evolving or slowly evolving with the time. On the other hand, the non-baryonic form of the octonic dark matter is evident through its gravitational effect only. However, from experimental point of view, the summary of the current measurement of the matter density, the dark matter density, and the energy density is already given by Hagiwara. And now each are the units in the critical density. Omega critical 3h square 8 pi g, where g is the Newton's gravitation constant, h is the present value of the Hubble's constant, which is also the cosmological constant here, cosmological parameter here. Now the experimental results require the basic current value for the matter and energy density. Omega matter, this is 0.27 and this is 0.73, and we have the difference omega matter minus omega baryon must be in the form of the non-baryonic dark matter, which is coming out to be 0.24. The range of the density of the matters within the standard cosmological model derived from the first released data with the corresponding values of the newest data is the Hubble parameter here. So you can just see here. Now octonic dark matter, it is the combination of the baryons plus hot and cold dark matter, which is consistently omega dark matter. Now however the dark matter can be classified either as hot and cold depending on whether it is relativistic or not in the early universe. So you can analyze the hot and cold dark matter in terms of the split octonics. We have the total octonic dark matter density, which is given by this equation 25. So the dark matter may be described in terms of the following 2 cross 2 John vector matrix realization of the split octonics, which is represented by equation 26, where this term representing an octonic field strength representing the hot dark matter. So these are the equations, and so the components has also been elaborated in equation 27. Now we have this J. What is it? Representing the non-baryonic octonic hot dark matter current density associated with the massless photons, graviton, etc. The current source equation for the octonic hot dark matter are given by equation this 29. This is visible to you. Now we have cold dark matter. Can be described as the composition of the massive object moving at subrelativistic velocities. Cold dark matter at the hot dark matter. What is the basic difference? When we just have the difference between these cold and hot dark matter is that the velocity of the octonic hot dark matter cause it to wipe out structure on the small scale. Now the octonic cold dark matter is associated with the electromagnetic, gravitational and gravitational electromagnetic and their mixed interactions. Now we have analyzed the octonic cold dark matter for the massive particles helium and GEM. That is equation 30 representing here. The cold dark matter represents the octonic field tensor associated with the cold dark matter, and reduced to the equation 30 the following components, where the mediators of the octonic cold dark matter are non-baryonic particles like WZ bosons here. Therefore, the current source density for the octonic cold dark matter are given by equation this 32 here. So we have this J cold dark matter describe the octonic. This cold dark matter is associated source density, which is associated with EMG and EMG field spaces, and these are the equation 33, which is the quantum equation for octonic hot and cold dark matter, and in the simple and compact octonic notification. From the foregoing analysis, we find that matter density of octonic cold dark matter that is lying between this range is greater than the octonic hot dark matter which is lying from this particular value. So we have the discussion here, result and discussion. So if we just see here, so octonic hot and cold dark matter may be easily expressed in terms of the, you can just say here, simple compact notation of the octonic representation. Matter density of octonic cold dark matter is greater than that of the octonic hot dark matter. There exists more cold dark matter than that of hot dark matter in nature, supported by the octonic field equation. So in this lecture, I have represented my topic. This is existence of dark matter in high dimensional division algebra. Uh, thanks to the you can just organize it, Dr. Ratnakar sir, for giving me opportunity for representing my lecture on the topic. So thanks to all of you. Thanks for your question. Thanks for listening. Thanks to all of you. Thanks to all.
Good afternoon. We welcome you all to the second day of this International Conference on Mathematical Advances and Applications 2020. Hope you all had a very good, successful and interactive session yesterday. Today also we promise that we'll have the best session, very informative and interactive from our experts. Today we have Dr. Ayaj Ahmed from Department of Mathematics NIT Patna. He will be speaking to us, followed by Dr. Selva Ganeshan, professor who worked in Malaysia earlier and now currently in JJ Engineering College of Science and Technology, Tiruchirappalli. They will be speaking to us, and after the speakers speak to us, we'll have a short discussion session where you can interact with the speakers. You may clarify or seek any question that you would like to clarify with them, know anything that you would like to. And after the speakers discussion session, we have closer to 10 to 12 people for presentation today also. After the presentations, we'll have interactive session among the audience, and at the end we'll have the certificate distribution and a short valedictory with the information regarding your certificates, publications, proceedings, etc. Once again, I thank you all for joining with us and keeping your trust into this conference, and we promise that you'll have the best session possible today also. Thank you all. Stay tuned. Thank you. We have in our midst Dr. S. Selva Ganeshan, Professor, Department of Information Technology, JJ College of Engineering and Technology, Tiruchirappalli, Tamil Nadu, India. Sir, we are happy to have you in our midst. Thank you for accepting our request. And as we recall your association with us longs back a couple of years ago. Dr. Selva Ganeshan obtained his master's degree in Information and Multimedia Technology from University Tun Abdul Razak, Malaysia. He is a full-time research scholar in the Faculty of Computing and Informatics, Multimedia University, Malaysia. He obtained his PhD in Information Technology from Multimedia University, Malaysia. With more than 28 years of teaching experience, about 15 years and more, he served in Malaysia as a professor. He has worked as a faculty in BITS Pilani, Rajasthan. In addition to his academic experience, he worked for more than 5 years in industry. He served as an assistant engineer in the government of Tamil Nadu for a small period. His field of interests include data mining, XML and databases, web technology and e-commerce. He published several papers in national and international journals and presented papers in national and international conferences. He has visited countries like Malaysia, Singapore, New Zealand for academic and research purpose. Thank you very much, sir, for being with us. Kindly speak to our audience. Thank you.
Good morning to one and all. I am Dr. Selva Ganeshan, Professor and Head, Department of Information Technology, JJ College of Engineering and Technology, Tiruchirappalli, Tamil Nadu. I welcome you all to my presentation on Computer Network Topologies, a comprehensive review. So again, I welcome you all to my presentation. Okay, my presentation will provide a deep understanding of the computer network topologies covering the following topics. Definition of topology, types of topology, pros and cons of each topology, choice of topology for businesses. Okay. So before going to details on the topic, let's see what is a network. A network is a set of devices connected by communication links. So the devices are normally referred to as nodes. Here the communication links may be wired link or wireless links. A node can be a computer, a printer, or any other devices capable of sending or receiving data generated by other nodes on the network. So that is a simple definition of a network. Okay. Furthermore, what is a computer network? A computer network is a group of interconnected computers. So maybe two or more computers are interconnected. Why we need networks? The question generally arises. So it allows the computer to communicate with each other and to share resources and information. So file sharing. You can easily share the data between different users or access it remotely if you keep it on other connected devices. At the same time, resource sharing using the network, connected peripheral devices like printers, scanners, and copiers, or sharing software between multiple users and save money. Of course, maybe you are all are aware that the best known computer network is the internet. Okay. So now we'll see the term and definition of physical topology. Of course, this presentation focuses on computer network topologies. Okay, first of all, we must know what is topology. The term topology refers to the way a network is laid out physically. Suppose we have two computers or three computers, easily we can make a network. So we can simply connect them. But we have a number of computers in our office or maybe in the college or maybe in the house. How to construct a network physically? That is a question. So we need some systematic approach. Two or more devices connected to a link. At the same time, two or more links form a topology. The best definition is the topology of a network is the geometric representation of the relationship of all the links and linking devices to each other. It's a geometric representation. So, though two organizations are identical, two networks are not exactly similar or same. There are many types of topologies. I'm moving to next slide. There are many types of topologies. Some of network topologies include mesh, star, bus, ring, and hybrid. So let us see one by one. First, we'll go through mesh topology. Of course, each device has a dedicated point-to-point link to every other device in the network. You can see the figure 1. Every device is connected to any other device in the network. So as a result, there may be more number of links. The links means cables. There are more number of links. So links are crossing each other and form mesh-like topology. So you can see figure 1. Figure 1 shows a fully connected mesh topology. So that one connecting 5 devices. In a mesh topology network with n number of nodes, there are n times n minus 1 over 2 direct links. At the same time, number of I/O ports for each device required is n minus 1. It is simple arithmetic formula. Okay. So in the mesh topology, the data is transmitted through the 2 methods, namely routing and flooding. Of course, you might have known about routing in computer networks. Routing is where data is routed to packet's destination in the shortest distance. But flooding is where data is sent to all nodes within the network. Okay, so mesh topology has both advantages and disadvantages. So now you can see here advantages of the mesh topology. So mesh topology are used first and foremost because they are reliable. So here you can see in the slides, mesh topology is robust, better privacy and security. Failure of one link will not disturb other links. Mesh topology helps the network manager to find the fault location and solution. These are the major advantages of the mesh topology network. But at the same time, mesh topology has some disadvantages. What are the disadvantages? Mesh topologies are far from perfect. They require an immense amount of configuration once they are deployed, because the links are crossing each other, large amount of cabling and I/O ports are required, installation and recommendations are reconnection are difficult, installation and reconnection are difficult. So these are some disadvantages. Okay, I'm moving to next topology, that is star topology. So star topology, you can see the figure 2. A star topology connecting 4 stations. So how you define, how we can explain star topology? Star topology has, in the star topology network, every device has a dedicated point-to-point link to a central controller hub, that is only, maybe a switch. You can see the figure 2. Every device is connected to any other device in the network through hub or through a central controller. So in a star topology network with n number of nodes, there are direct n links. Say in this figure 2, there are 4 devices, means there may be 4 direct links. Direct link, there are 4 links. Okay, similarly here, like mesh topology, star topology also has both advantages and disadvantages. So advantages, as far as the advantages are concerned, star topologies are most commonly used because we can manage the entire network from one location, that is central hub. isn't it? So easy to control. So that's why star topology is most commonly used. What are the other advantages? Star topology is robust, less expensive. Fault identification, fault isolation are easy. Modification of star network is easy. These are some advantages. So when you talk about disadvantages, though star topologies may be relatively safe from failure, if the central switch or central hub goes down, then the entire network will go down. I hope you can follow my presentation. If the central hub fails, the entire network will not work. So that is the major disadvantage. Another one is communication is possible through the hub because all the devices are connected through central the device, that is hub. So all the communication is possible through the hub. Okay, so this is something about star topology. Then I'm moving to third type, bus topology. So what do you mean by bus topology? You can see the figure 3, a bus topology connecting 3 stations. The figure 3 shows a bus topology connecting 3 stations. So how we can explain? So bus topology is a network type where every device is connected to a single cable that runs from one end of the network to the other. This type of network topology is often referred to as line topology. So normally in your bus topology, the data is transmitted in one direction only. If the bus topology has 2 endpoints, then it is referred to as linear bus topology. These are some fundamentals about the bus topology. You can see in the figure 3, there is a long cable. One long cable, that one is acting as a backbone to link all the devices in the network. Nodes are connected. That is, a node means a station or device, anything. So nodes are connected to the backbone by taps and drop line. Drop line is establishing the connection between devices and the cable. The taps are used as the connectors. So this is the bus topology structure. But bus topology has some advantages. At the same time, the bus topology network has some disadvantages. Okay, as far as the advantages of the bus topology are concerned, bus topologies are often used in smaller networks. Why? Because the layout is very simple. The bus topologies often used in smaller network. The main reason is that bus topologies keeps the layouts very simple. So easy installation, less cabling, and less number of I/O ports is required. Also less cost. These are the advantages. As far as the disadvantages of the bus topology are concerned, what are the disadvantages? Relying on one cable, isn't it? But there is a long cable in the bus topology acting as a backbone. So the whole bus topology network depends on the one cable. That means bus topologies have a single point of failure. If the cable fails, the entire network will go down. So that is major disadvantage. If the long cable fails, the entire network will go down. So other disadvantages are network traffic is high, fault isolation, reconnection is difficult. Adding new device is difficult. Also, a break in the bus cable stops all transmission. So bus topology is used for small business because of the very simple layout. Okay. Then I'm moving to next type of topology, that is ring topology. Okay, ring topology. So in ring topology, computers are connected to each other in a circular format. Every device in the network has two neighbors only. Ring topologies were commonly used in the past. The past ring topologies were commonly used. Today, ring topology is rarely used in business organization. We can see the advantages and disadvantages. Before that, now you can see the figure 4. Figure 4 shows a ring topology connecting 6 stations. Example, each device has a dedicated point-to-point link with only 2 devices on either side of it, neighbors. A signal, for example, a signal travels along a ring in only one direction from device to device until it reaches its destination. The repeater is used to regenerate the signals during transmission because the signal travels until it reaches destination. So sometimes the signal become weaker. So every station, so along the ring, there is a repeater. The repeater job is to regenerate the signals during the transmission. So the signal will be very strong and not faded. So that is the unique feature of the ring topology here. Okay, then what are the advantages and disadvantages? Okay, here with ring topology, the risk of packet collision is very low because it is traveling in unidirectional. So it is traveling along the ring. So also it is easy to install and reconfigure. Link failure can be easily found out. These are some advantages. But disadvantages, ring topologies were replaced mainly because they are very vulnerable to failure. If one node fails, the entire network will be out of operation. Very major disadvantage. The major disadvantage is the one node failure or failure in one node will lead to entire network failure. So other disadvantages given in this slide, maximum length of ring and number of devices are limited. Failure of one node on the ring affects the entire network, already I told. Addition of nodes or removal of nodes disrupts the network. Signal traffic is unidirectional. Only one direction only the signal will travel. These are some disadvantages. So normally in a ring topology network with n number of nodes, there are direct n links. So for example, there are 4 computers in the ring topology network. Then the number of direct links in the network should be 4. So it is a simple logic. Okay, then I'm moving to next type of topology, that is hybrid topology. So hybrid, the term itself is self-explanatory. So the hybrid topology is a type of network topology that uses 2 or more other network topologies, including bus topology, mesh topology, ring topology, or star topology. So as I mentioned earlier, hybrid topology is composed of 2 or more different topologies. Hybrid topologies are most commonly used in larger organizations where individual departments have different network topology. Maybe you take the very large organization, very big companies. There are a number of departments. Maybe each department has different network topologies. All these network topologies connected together and form hybrid topology. That is the concept. The figure 5 shows a hybrid topology, a star backbone with 3 bus networks. You can see the 3 bus networks all together form hybrid topology. Okay, there is a hub. So star backbone with 3 bus networks. There are 3 bus networks with a hub. That's why it is a hybrid topology. Okay, see another example. Figure 6 shows a hybrid topology, a star backbone with different networks, namely bus, ring, and star topology networks. So this is a typical example for hybrid topology network. Okay. Then we are moving to next slide. Okay, now, so all the types of topology we already discussed. The first one, star topology. So first one, mesh topology. Second one, star topology. Third one, bus topology. Fourth one, ring topology. Fifth one, hybrid topology. Okay, now the question is, there are 5 or 6 types. One more topology, sometimes some people say tree topology. So among all these type of topologies, which one we can choose for our organization or our business organization? So that is a question. So that one we need to answer. Before choosing a topology, some factors will be considered. What are the factors? You can see in the slide. You can see in the slide. Length of cable needle, cable type, cost, and scalability. First, we need to take into consideration the length of cable. We need to provide service to network devices. A bus topology is most lightweight in terms of cable needs. In this context, the bus topology is the simplest topology to install and buy the cables, everything. So maybe the cost is so very low. So the length of the cable should be considered. Second factor, cable type. We have to consider the type of cable we are going to use. Cable types may be twisted pairs, coaxial cable, and optical fiber cables. Third factor is cost. The cost of installing the topology is also very important. If you use more complex topology, the cost of installation is obviously more. So the cost plays a crucial role. The fourth factor to be considered is scalability. Suppose we want to increase the number, increase the size and quality of network infrastructure later. It should be easy to add devices too. Now, scalability is also very important. So before choosing a topology for the business organization, these factors are to be considered. Okay. Then I'm moving to next slide. Still some more, choosing topology. So choosing the topology, how to choose topology? depends on the requirements of usage. So for what usage we are going to use the network, whether it is a heavily used or very maybe in a lower loads, depends. At the same time, number of nodes in the network. Suppose we have a 10 system, we make a network. So it is a different one. We can simply go for a symbol topology, like bus topology. Or maybe we have a more number of system, also all heavy usage of the networks. Then we go for some complicated topologies like mesh or hybrid topology. So already I explained in the previous slide, each topology has its advantages and disadvantages depending on the environment in which it is being deployed, isn't it? So this all play the role in choosing the network topology. But however, the best network topology for large businesses, so because very big organization, more people using more system, so number of tasks to be completed. So in this case, the best network topology for large businesses organization is the star topology. Already I told in the star topology explanation, the reason is it is easy to manage the entire network from one location, that is central hub. Every device is connected to any other device in the star topology network through a central hub. So control is easy. So the best network topology for large businesses is by and large star topology. Okay. Then at the same time, reliable network topology for smaller businesses, reliable, or we can say cheap. For smaller businesses network, bus topology are good and cost-effective choice. Bus topology, already I told, bus topology, it keep the layout very simple. The design and arrangement is very simple because there is a long cable. With that cable, system or devices are connected simply. That's all. The reason is that layout is simple. It allows all the devices to be connected via single coaxial or RJ45 cable. That's all. If needed, sometimes they want to add more nodes. So the node can be easily added to the network by joining an additional cable. So it's quite easy. So layout also very simple. Also, you can add more node also, you can simply join additional cable. So for smaller businesses or for the cost effective situation, then go for bus topology. Okay. So this presentation has provided a broader insight into the definition of topology, types of topology, advantages and disadvantages of each topology. Furthermore, choice of topology for businesses. Of course, hope my presentation provides the broader insight into the computer network topologies. So this is a very brief explanation. So within the limited time. So before closing my presentation, I would like to extend my sincere thanks to Professor Dr. Ratnakar D. Bala and all staff members of Red Talks for having given me this opportunity to do this presentation. Thank you.
Thank you, sir. We now have in our midst Dr. Ayaz Ahmed, Assistant Professor, Department of Mathematics, NIT Patna, India. Dr. Ayaz Ahmed a serious researcher and scholar in mathematics and a long associate of IMRF, currently serving in National Institute of Technology, Patna, published many papers in national and international conference, traveled across India to deliver talks, and he has delivered many talks in IMRF platform too. Thank you very much, sir, for accepting our request and joining us in this international conference. Kindly speak to our audience, sir. Thank you. We now invite Dr. Basaya B. Mathad, Assistant Professor, Department of Mathematics, ESG, Balakundur Institute of Technology, Belgavi, Karnataka, India, to kindly present his paper. Sir, kindly please.
Hi, hello. Myself, Dr. B.B. Mata, from Department of Mathematics, SC Balakuntra Institute of Technology, Belagavi, Karnataka, India. Okay. Today I want to present my one of the new work. It is on the fuzzy topological spaces and entitled with the some studies on fuzzy generalized regular open set. Okay, and it is a collaboration with work with the professor the Rakesh Humadi, and he is also from the same department. And okay, uh, the overviews. The content of the paper is the abstract and the introduction, and the third one is preliminary, and the fourth one is the main topic. It is a fuzzy generalized regular open sets. The last one is the reference. Okay. And the abstract of this paper is we introduce important fuzzy generalized open set, namely it is the fuzzy generalized regular open set. Okay, in briefly you may call it as the fuzzy GR open set. And along with this, and we will expound the fuzzy GR neighborhood fuzzy GR. It is a continuous, as well as we will study the properties of the respective. It is a newly developed. It is a concept. Okay, the keywords of this work is it is a fuzzy GR open set and fuzzy GR neighborhood fuzzy GR. It is a continuous. And the introduction as the Ajad Balsubramaniam Manian and the Jede Charin, and introduce the generalized fuzzy, the closed sets, namely you may call it as a fuzzy G closed set and the fuzzy semi-open set and fuzzy regular semi-open set, as well as the fuzzy delta open set by the size XL et al. Okay. The Balasubramaniam introduced the fuzzy G closer as well as the fuzzy G interior. Okay, and recently, yes, Dr. Nirani Lakshmi and B.B. Matar and R.S. Wali introduced the new concept. It is a GR open set, GR closed set, GR neighborhoods, and the GR continuity in their work in the general topological spaces. But the aim of this paper is to introduce and study the notion of the fuzzy GR open set and the in the fuzzy topological spaces. And the same concept in the fuzzy topological spaces. And the preliminary jar, it is a fuzzy regular open set, and it having its own expression as gamma is equal to interior closure of it is a gamma. And similarly fuzzy semi open, and it is here as the gamma is subset of it is a closure interior of it is a gamma. And similarly the fuzzy regular semi open and fuzzy phi open, and these are all essential. It is a parameters to develop the new concept in the fuzzy topological space, and its name is the fuzzy GR open set and their property. Yes, and the definition of the fuzzy GR open set is You may consider the subset, it is a gamma of fuzzy space, it is a X, is said to be it is a fuzzy GR open set. It should obey the one expression, mathematical expression, the gamma should be is equal to the fuzzy interior fuzzy Z closure of it is a gamma. Okay, and we denote the family of the GR, it is a the fuzzy GR, it is a open set, it is a FGRO of this X. Okay, and the properties of the fuzzy GR, it is a open set is every fuzzy regular open set is it is a the fuzzy GR open set, and which shows the stronger properties in the it is a fuzzy topological spaces. And the similarly the next property is it is a every fuzzy GR open set is a fuzzy open set, and the implication between the open set as well as the regular open set is the fuzzy regular open set is it is always a fuzzy GR open set, and the every fuzzy GR open set is it is a fuzzy open set. The conversely it is a not true one. Okay, the next one is the intersection between the two fuzzy GR open set is again it is a the fuzzy GR open set, and which does not obey the union between the two fuzzy GR open set. Okay, the theorem number, say this is one of the important, it is a property. If suppose you may consider the one fuzzy subset, it is a gamma is, it is a fuzzy GR open set, and it shows the relationship between the F interior, fuzzy interior of gamma is equal to it is a gamma. And similarly, the complement, the remark shows the complement of the fuzzy GR open set, it is need not be a, it is a fuzzy GR, it is a open set. Okay, then next, it is a complete complementary concept of the fuzzy GR, it is a open set. Okay, the definition of the fuzzy GR open set is GR closed set is, suppose you may consider as the gamma is it is a fuzzy GR, it is a open set, and its complement 1 minus of gamma is it is a fuzzy GR, it is a closed set in it is a X. And these are all some the properties. And the property number one, a fuzzy subset, it is a gamma of X is said to be it is a fuzzy GR, it is a close if and only if it should obey the gamma is equal to F closure of FZ interior of it is a gamma. And the one more the result is if gamma is a S fuzzy GR closed set, and if and only if it should obey the F closure of gamma is equal to it is a gamma when the gamma is a fuzzy GR, it is a close. And the one more result is means one more it is a concept as fuzzy GR in neighborhoods as well as it is a fuzzy GR, it is a interior. And definition of the it is a fuzzy GR in, neighborhood is nothing but may consider the as a XPA fuzzy topological space, and you may choose the one point from the it is a X, and XPA one of the point of the it is a X, and a fuzzy subset gamma of X is said to be it is a fuzzy GR neighborhood, or else briefly we may call it as a FGR, it is a neighborhood of it is a X if and only if there exists the fuzzy GR open set, and the existed open set is like that X is a element of it is a the one it is a fuzzy GR open set epsilon, and is a subset of it is the gamma. Okay, the next one is the collection of all fuzzy GR neighborhoods of the particular point X in the X is called it is a fuzzy neighborhood system at the point it is a X, and which is denoted by FGRN of it is a X. Okay, and the next one is okay. The analogs to fuzzy interior in the fuzzy space X, we define the fuzzy interior, GR interior in the fuzzy space it is a X. And then here there is the definition of the fuzzy GR, it is a interior. As mathematically we may call it as if the gamma is a subset of the fuzzy subset of it is a X is said to be it is a fuzzy GR interior of it is a gamma, which shows the fuzzy union of all the open set, and all the open sets are it is a in the fuzzy GR it is a open set, means that is nothing but the pi is it is a subset of it is a gamma. Okay, and these are all some important properties relating to relating with the it is a fuzzy GR interior. The first one is gamma and the pi are the fuzzy two fuzzy subsets of it is a X, and which having the FGR of interior of it is a 1 is equal to it is a 1 because of, and the membership function is completely defined in between the 0 and it is a 1, and which attains the supremum value as the 1, and similarly FGR of interior of 0 is equal to as it is a 0, and similarly FGR interior of gamma is subset of it is a gamma. And if the pi is any subset for any fuzzy or GR open set contained in the gamma, then which obey the pi is subset of for G, FGR of interior of it is a gamma. Okay. The fourth one is if the gamma is subset of it is a pi, then FGR interior of it is a gamma is less than or equal to FGR interior of it is a phi. And the last one is the FGR interior of the fuzzy generalized regular interior of gamma is always is equal to the FGR interior of it is a gamma. Okay. The next definition shows the let the gamma is a fuzzy subset of it is a X, and we define the fuzzy GR closure, and which is completely as expressed as the FGR of it is a closure of it is a gamma is equal to intersection of the intersection of it is a all the subsets of fuzzy subset it is a gamma such that it is a gamma is less than or equal to, or else you may call it as a the fuzzy subset of it is a pi, and which is belongs to the family it is AFGRC of is a X. Okay. The next important concept is fuzzy GR continuous maps and their property, and directly we will define the fuzzy GR it is a the continuous by the inverse image of the every fuzzy closed set in the Y is it is a the fuzzy GR closed set in it is a X. With the help of this definition, we will solve the one property. Okay, the inverse image of the as the fuzzy open set in Y is a it is a fuzzy GR open set in it is a X. If and only if SEF is a it is a fuzzy GR continuous. And the next definition it is a fuzzy GR open set. Okay, and we will define here the image of the every fuzzy open set in X is a it is a fuzzy GR open set in it is a X. Okay, and the last one is it is a the fuzzy GR it is a open mapping. Okay, and it is also follow with the definition of the fuzzy GR it is a closed set. Okay, and the F is to a fuzzy map S, and fuzzy GR it is a open map, then it obey the say this is the as it is the fuzzy open it is a map. Okay, and the last definition is the fuzzy generalized regular homomorphism. Okay, simply we may call it as a fuzzy GR homomorphism, and it is defined as the F is a fuzzy GR continuous and F is a fuzzy GR it is a open map. With the help of this definition, and we will prove the every fuzzy GR homomorphism is it is a fuzzy homomorphism. And this is the end of my presentation, and these are all the some important references. Okay, thank you so much.
Thank you, sir. We now invite Dr. Deepali B. Banswal, Assistant Professor, BP Arts, SMA, Science and KKC Commerce College, Chalisgarh, Jelgarh, to kindly present her paper. Madam, please.
Good evening to all. Myself, Dr. Deepali Banswal from Department of Mathematics, BP Arts, SMA Science and KKC Commerce College, Chalisgarh. Today's my topic of presentation is generalized supplemented lattice. Now, outlines are introduction, preliminaries, GS lattice, GAS lattice, and GWS lattice. GS lattice is generalized supplemented lattice, generalized ample supplemented lattice, and generalized weak supplemented lattice. Fourth out is closed weak generalized supplemented lattice. And references. Introduction. The concept of a supplemented module and its generalization is studied by several authors like Mutlu, Mohammad Tohidi, Wang and Ding, Bisauer, Zenitel, and many others. In this paper, we introduce the concept of generalized supplemented lattice, a generalized ample supplemented lattice, and a generalized weak supplemented lattice, and obtain results in the context of modular lattices. We also introduce the concept of a closed weak generalized supplemented lattice and obtain results in the context of modular lattices. We replace the condition of an extending lattice, that is any closed element in a direct summand, by the condition that any closed element has a weak generalized supplement. Thus, we generalize both an extending lattice and a weak generalized supplemented lattice to a closed weak generalized supplemented lattice. Throughout in this paper, L denotes a modular lattice with 0. And whenever necessary, we assume that rad of A exists for any element A belongs to L and rad of L equal to 1. And for ideal, rad of I for any ideal I. Okay. Now preliminaries. Preliminaries, we know the basic definitions of modular lattice, complete lattice, small, supplement, ample supplement, weak supplement, direct sum, essentially closed, extending, now generalized supplemented ideals. Now first of all, we will see what is radical. So what is radical? In the lattice, the intersection of all maximal ideals. Okay, intersection of all maximal ideals in L is called the radical of L, and it is denoted by rad of L. Now generalized supplement means let L be a lattice, let Ij belongs to idea of L, means Ij belongs to lattice of ideals, and there is ideal I and j which are non-zero, be such that I join j equal to L. Then J is called a generalized supplement of I in case I intersection J is subset of, is contained in rad of J. Now a lattice L is called a generalized supplemented lattice if every ideal in L has a generalized supplement in L. In short, we say that L is a GS lattice. Now, in the lattice L shown in figure 1, here we considering ideal I3. What is I3? 0AD and I4 0ACE, such that I3 join I4 equal to L. But I3 intersection I4 does not contain in 0, which is equal to rad of I4. Hence, I4 is not a generalized supplement of I3. And for consider for ideals I1 0A and I2 0CF, I2 is generalized supplement of I1. Now, generalized ample supplemented lattice. A lattice L is called a generalized ample supplemented lattice if L equal to I join J, where Ij belongs to lattice of ideals, implies that I has a generalized supplement K such that K is contained in J. Now here in the lattice shown in figure 2, I1 is 0D and I2 is 0ABE. So I2 is a generalized ample supplement of I1 in L. Now weakly generalized supplemented lattice. A lattice L is said to be a weakly generalized supplemented lattice if for any ideal I and non-zero there exists J such that I join J is equals to L, such that I intersection J contained in rad of L. In short, we said that L is WGS lattice, means weakly generalized supplemented lattice. So in figure 3, consider I1 equal to 0 AB and I2 equal to 0 ACDG. So I2 is weakly generalized supplement of I1. And consider I3 0 ABDF and I4 0 ABCE. So I4 is not a weakly generalized supplement of I3. Here are some theorems we have proved for GS lattice. These are theorems. Now, generalized direct sum supplemented lattice. A lattice L is called a generalized direct sum supplemented lattice if for every ideal I of L has a generalized supplement which is a direct summand of L. Okay. So in short, we say that L is a G direct sum S lattice. In short, we say. Now, in the lattice L shown in figure 4, I consider ideal I1 0 AD and I2 0 ACE such that I1 join I2 is equal to L and I1 intersection I2 is a subset of content in 0A, which is equal to 0A is rad of I1. That is, I1 is a generalized supplement of I2 and also I1 is a direct summand of L. Hence, I1 is a generalized direct sum supplement of I2. Now, these are theorems, proof for generalized supplement. Now, completely generalized direct sum supplemented lattice. A lattice L is said to be completely generalized direct sum supplemented lattice if every direct summand of L rather than minimal ideal is a generalized direct sum supplemented ideal. We are considering direct summand which is not minimal ideal. Okay. So now, in the lattice L shown in figure 5, consider ideal I1 0 ABE and I2 0 CDF are direct summands of L. Now here 0A join 0B is equals to I1 such that 0A intersection 0B is 0, which content in rad of 0B and 0B is a direct summand of I1. Hence, we can verify for I2 also. Hence, L is a completely generalized direct sum supplemented lattice. Now, this is theorem. Now, closed weak generalized supplemented ideals. Now, let L be a lattice and ideal I belongs to ID of L is called closed weak generalized supplemented ideal if for each closed ideal J in I there exists an ideal K contained in I such that K join J equal to I and K intersection J is contained in rad of I. In short, we say that I is a CWGS ideal. Now, a lattice L is called closed weak generalized supplemented if for any closed ideal I belongs to ID of L, there exists an ideal J such that L equal to J join I and J intersection I is contained in rad of L. In short, we say that L is CWGS lattice. We have considered these definitions for ideal also and for lattice also, and we can generalize this for elements also. Now, in the lattice L shown in figure 6, consider the ideal I 0A B C F and ideal I1. 0A content in I is closed in I. Okay, I1 is closed in I. Then there exists I2 0C which is also contained in I, such that I1 join I2 equal to I and I1 intersection I2 is ideal generated by 0 and rad of L is 0, means ideal generated by 0. Thus we can verify for all closed ideals in I. Hence I is a closed weak generalized supplemented ideal. Now these are theorems. Every weak generalized supplemented lattice is a closed weak generalized supplemented lattice. Firstly, we have proved that weak generalized supplemented lattice is a weak generalized supplemented lattice, closed weak generalized supplemented lattice. Every extending lattice is a closed weak generalized supplemented lattice. Every generalized supplemented lattice is a closed weak generalized supplemented lattice. So these theorems we have proved for closed weak generalized supplemented lattice. Now we show that closed weak generalized supplemented lattice is equivalent to extending lattice by taking condition rad of L is 0, ideal generated by 0, and let L be a closed weak generalized supplemented lattice, then any image of L is also a closed weak generalized supplemented lattice. Now these are references we have used. Thank you.
Thank you, madam. We now invite Ms. T. Sunita, lecturer in mathematics, Government College for Women, Kurnool, Andhra Pradesh, to kindly present her paper.
Sunita, lecturer in mathematics, Government College for Men, Kurnool. My topic is strongly regular ternary semigroups. Before going to my topic, let me introduce something. The formal study of semigroups began in the early 20th century. The term semigroup first appeared in the literature of J.A. D. Silver book, Elementary Law Theoretic Groups, abstracted in 1904. 1970, the notion of regular semigroup introduced by T. Hall. After that, G. Mason studied strongly regular near rings in 1980. We then studied the generalization of strongly regular ternary semigroups in 1986. Recently, Jane Tang and Jiang Xi studied on fuzzy quasi-ideals of ordered semigroups. Characterization of strongly regular ordered semigroups and characterization of left and right simple ordered semigroups. This paper mainly deals with the different ideals like fuzzy quasi-ideals, fuzzy completely semi-prime ideals in strongly regular ternary semigroups. Okay, let me introduce some definitions. So what is ternary semigroup? A non-empty set T is said to be ternary semigroup if there exists a ternary operation dot T cross T cross T to T written as A, B, C implies A into B into C on T, where dot is closed under multiplication. Dot satisfies the following identity: ABC of DE is equal to A of BCD of E, that is equal to AB of CDE for any A, B, C, D, E belongs to T. These two are examples of ternary semigroup. Okay, let us see another definitions. So a ternary semigroup T comma dot is called left, right, lateral regular if for each A belongs to T there exists X comma Y belongs to T such that A is equal to A cube XY. Then the ternary semigroup is called regular left regular ternary semigroup. Clearly, a ternary semigroup T is strongly regular if and only if A belongs to TTE cube intersection A cube TT intersection T A cube T for every A belongs to T. So a non-empty subset A of a ternary semigroup T is called left ideal in T if TTA contained in A. Similarly, for right ideal, ATT contained in A and lateral ideal TAT contained in A. Okay, so what is quasi-ideal in T? A non-empty subset A of a ternary semigroup T is called quasi-ideal in T if ATT intersection TAT intersection TTA contained in A and ATT intersection TTA intersection TTA contained in A. So let me explain what is fuzzy set and what is fuzzy quasi-ideal. Let X be a non-empty set. A fuzzy set F of the set X is a function F x2 0, 1. A fuzzy set F belongs to F of T is said to be fuzzy left ideal of T if f of x, y, z greater than f of z. Respectively, right ideal f of x, y, z greater than or equal to f of x and lateral ideal f of x, y, z greater than or equal to f of y. For all x, y, z belongs to T. Okay. Let me introduce some theorems which I have used in proving the theorem which I have proved. Okay, if F1 and F2 are two fuzzy subsets of non-empty set T, then F1 intersection F2 circle T contained in F1 circle T intersection F2 circle T. Second one, T circle F1 intersection F2 circle T contained in T circle F1 circle T intersection T circle F2 circle T. So third one is T circle F1 intersection F2 contained in T circle F1 intersection T circle F2. So F is a fuzzy left ideal in ternary semigroup T if and only if T circle F contained in F. Similarly, for right and lateral ideal also, next theorem will explain. Okay. So coming to the theorem. So what is the theorem? Statement is, let T be the ternary semigroup and F be a fuzzy subset of T. Then F is a fuzzy quasi-ideal of T if and only if all non-empty level subsets T belongs to 0, 1 are quasi-ideals of T. Here, first I took F is a fuzzy quasi-ideal of T. Then I proved that the non-empty level subset T belongs to 0, 1 are quasi-ideals of T. Conversely, I took non-empty level subset T belongs to 0, 1 are quasi-ideals of T. Then I proved F is a fuzzy quasi-ideal of T. So see here, first I took that. So T is a ternary semigroup and F is a fuzzy subset already given. So I took F is a fuzzy quasi-ideal of T. So fuzzy quasi-ideal of T by hypothesis, f of x greater than or equal to F circle T intersection T circle F circle T intersection T circle F of x. By taking all these, we will get that x belongs to Ft. So FTT intersection TFTT intersection FTT contained in Ft. Similarly, we get FTT intersection TTFTTT intersection FTT contained in Ft. So hence, so Ft is a quasi-ideal of T. So in conversely, what I took Ft is if Ft is a quasi-ideal of T, I proved that T is a quasi-ideal. See here, sorry, F is a fuzzy quasi-ideal. So suppose, so I took that Ft is a non-empty quasi-ideal of T. So since it is a non-empty quasi-ideal of T, F circle T intersection T circle F circle T intersection T circle F of x less than or equal to F of x. So by all this one, finally here I proved that FTT intersection TFTT intersection FTT contained in Ft. So moreover, let x, y belongs to T if x less than or equal to y, then f of x greater than or equal to f of y. Since Ft is a quasi-ideal of T, so we have x belongs to f lambda, then f of x greater than or equal to lambda, that is equal to f of y. Therefore, f is a fuzzy quasi-ideal of T. Okay, coming to the second theorem. What is second theorem? Let T be a ternary semigroup, then the following statements are equivalent. T is strongly regular. For each fuzzy quasi-ideal of T, f of a is equal to f of a cube for any A belongs to T, for each fuzzy quasi-ideal of quasi-ideal f of t, f of a power n is equal to f of a power 2n plus 1 for any a belongs to t, n belongs to z plus. So fourth one is every fuzzy quasi-ideal f of t is completely semi-prime. So these four are equivalent. So I proved, I took first two, that is, if t is a strongly regular, I proved that for each fuzzy quasi-ideal f of t, f of a is equal to f of a cube for any a belongs to t. So here I took that, I proved that f of a is equal to f of a cube. And also I proved 2, 2, 3. What is 2, 2, 3? If for each a fuzzy quasi-ideal f of t, f of a power n is equal to f of a power 2n plus 1 for any a belongs to t, n belongs to z plus, then every fuzzy quasi-ideal f of t is completely semi-prime. See here, so here it is clearly proved that, so completely it is t is a completely semi-prime. For 3 to 2 and 2 to 4, obviously we can prove that. So 4 to 1, what is 4 to 1? If every fuzzy quasi-ideal f of t is completely semi-prime, then t is strongly regular. See, I took here, hence finally a is equal to a cube, t a cube, t a, which is strongly regular. So conclusion. Fuzzy ideal of ternary semigroups may give different directions in the field of research of fuzzy ternary algebra. So further study of fuzzy ideal theory in ternary semigroups may explore the solutions of many interesting problems of ternary semigroup, which will play important role both in theory and applications in the future research of fuzzy ternary algebra. So these are the references which I took for to prove the theorem. So finally, thank you.
Thank you, madam. We now invite Ms. Sulochana Bereka, Research Scholar, Department of Mathematics, Acharya Nagarjuna University, Guntur, Andhra Pradesh, to kindly present her paper. Madam.
This is Sulochana. I'm a research scholar. I'm pursuing PhD under the guidance of Professor Beri Victor Babu, Acharya Nagarjuna University, Andhra Pradesh, India. Here I'm going to present my paper titled Measure of Flow Predictability for Second Order Response Surface Designs and an Interclass Correlative Structure of Errors using Central Composite Designs. In the design of experiments, for estimating the slope of the response, flow predictability is a desirable property. In this paper, measure of flow predictability for second order response surface designs using central composite designs under interclass correlated structure of errors is suggested and illustrated with different examples. Coming to the introduction, response surface methodology is a collection of mathematical and statistical techniques useful for analyzing problems where several independent variables influence a dependent variable. The independent variable is called input or explanatory variable and the dependent variable is called response variable. An important step in the development of response surface methodology is introduction of rotatability that is done by Box and Hunter in the year 1957. Das and Natsimum constructed the second order slope rotatable designs in the year 1962. Victor Babu and Nassim studied second order slope rotatable designs in the year 1991. Victor Babu 2007 suggested a review on actually basic work is introduced by Haddon Park in the year 1978. The slope rotatability second order slope rotatable central composite designs introduced by Haddon Park in the year 1978. Victor Babu and Nassim studied second order slope rotatable designs using balanced incomplete block designs in the year 1991. Park and Kim introduced measure of flow predictability for the second order response surface designs in the year 1992.
Sureka and Winter Babu studied measure of rotatability for second order response surface regions using central composite design. Many others have studied the rotatable designs and slope rotatable designs, assuming errors to be uncorrelated and homoscedastic. Um, in, prac- in practical situations, we have arises some situations that errors are correlated, evaluating the usual assumptions. To overcome these assumptions, thus introduce the robust robust second order rotatable designs in the year 1997, 1990, and 2003. And he introduced the slope rotatability with correlated errors and gave conditions for the different variance covariance structures in the year 2003b. Das and Park 2009 introduced the measure of slope rotatability for second order response surface designs. Rajalakshmi 2014 studied some contributions to second order response surface designs under different correlated structure of errors. Rajalakshmi and Vector Babu studied SOSRD under intra-class correlated structure of errors using CCD, symmetrical unequal block arrangements with two unequal block sizes BIBD respectively. In this paper, we follow the works of Park and Kim Das 2003b 2014, Das and Park 2009, Sureka and Victor Babu 2011, Rajalakshmi and Victor Babu. The measure of slope rotatability for second order response surface designs using central composite design for correlation quotient rho and k different factors is suggested. Second order response surface design with correlated errors. Here equation 2.1 represents the second order response surface model, and here B naught, Bi, Bij, Bii are parameters of the model, and Yu is the response observed response, and Yu is observed response in the youth design point. Conditions for the second order response surface designs with correlated errors, we have the variance of the estimated first order derivative with respect to each independent variable xi. Here 2.4 will be the function of s square that equal to summation I equal to 1 to k summation ui square if and only if the design have the following conditions. These are the slope rotatability conditions for this correlated errors. Equation 2.5 and 2.6 are slope rotatability condition. Here A1, G, F, E, N, eta are constant, and the variances and covariances of the estimated parameters of the model will be follows. 2.7 is variances and covariances of the estimated response of estimated parameters of the model slope rotatability for the second order model with correlated errors. By using 2.7 B naught, we have a non-singularity condition, that is B is greater than 0. If B is greater than 0, then only the design exists. Otherwise, the design will not exist. For this second order slope rotatability with correlated errors, we have a condition that variance of B hat equal to 1 by 4th of variance of Bij. Using 2.7, by substituting 2.7 in 2.9, we get a slope rotatability condition. We find the slope rotatability condition. This is slope rotatability condition for the correlated errors. This is variance of y hat. This is s square equal to summation I equal to 1 to k xi square. Here g and f are taken from the 2.7. These conditions are taken from DAS 2003b and 2014 DAS and POS 2009. This is the intra-class correlated structure. Conditions for the slope rotatability. These are the conditions of the slope rotatability with the intra-class correlated structure of errors. These are the simple symmetric conditions. These are the parameters of the intra-class correlated structure of errors. Here C equal to 3 eta and gamma 2, gamma 3 and eta are constant. If rho equal to 0, then the condition will become SOSRD you under under with errors are uncorrelated and homoscedastic. This is the slope retractability condition under intraclass correlated structure of errors. This rises when we substitute these parameters and simple symmetry conditions in 2.9, we get this equation. If rho equal to 0, this equation will become SYSRD uncorrelated homoscedastic case, that is Victor Babu and Nasimum 1991. This is the result which is taken from Rajalakshmi 2014. Here we have we use the central composite design. Central composite designs are obtained by adding suitable factorial combinations and 2k fractional replicate. If no interaction with less than 5 factors is confounding and 2 additional points is confounded. This is the result. This is taken from the Rajalakshmi 2014. This is my main concept. Measure of second order slope retractability for general correlated structure. These are the conditions for the measure of slope retractability. If these conditions follow, then the measure will be existed. MKD equal to 1 by 1 plus QKD. This is the proposed measure of slope retractability with intraclass correlated structure of errors. For any general covariance structure, this is the measure. MKD equal to 1 by 1 plus QKD. QKD is calculated from this equation. Then QKD becomes 1 by sigma 4 into variance of BI minus variance of BJ whole square. If MKD is 1, then only the design is slope retractable. If MKD approaches to 0, then the design is deviates from the slope retractability. Measure of slope retractability for second order response surface designs and intraclass correlated structures using central composite designs. Here we follow the works of Dasan Park, Sureka and Victor Babu. The proposed measure of slope retractability for second order response surface designs under interclass correlated structure of CCD is given below. These are the total number of actions n equal to f plus c. Here f equal to 2 power t of k and t equal to 2k plus n naught. These are the simple symmetry conditions of CCD. This G value is taken from 2.7. If MKD is 1, then the design is slope retractable for intraclass correlated structure of errors in CCD for all values of rho. MKD approaches to 0, then the design is deviates from the slope retractability with CCD. We illustrate this method with an example. Here we take 3 factors and these are simple symmetry conditions, and here we calculate gamma 2, gamma 4 and C values by using 4.6, and we get the biquadratic equation from the result to 3.1, that is taken from the Rajalakshmi 2014. This is the biquadratic equation. By solving this biquadratic equation, we find the A value 2.4324, and then here we calculate QKD is 0 and MKD equal to 1. So MKD equal to 1, the design is slope retractable. If we take alpha equal to 1.9 instead of taking alpha equal to 2.43, we get these values. So MKD is deviates from the slope retractability. In the table 1, we gave the measure values for different factors 2 to 17 with for correlation coefficient rho 0 to 0.9. We find this weak slope retractability region. MKD is greater than or equal to V. The slope retractability region is rounded for 0.95. We are able to give the weak slope retractability region. These are the table values. Here we calculate the 2 to 17 factors. This is weak slope retractability region. This is also calculated for 2 to 17 factors. For increasing the alpha and rho values, the slope rotatability value will be increased. In this paper, we measured the slope rotatability for second order response surface regions with intra-class correlated structure of errors for different factors. By increasing the alpha and rho values for different factors, the measure value will be increased. These are the some of the references that can be used to prepare my paper. I thankful to the organizers for giving this opportunity. Thank you.
Thank you, madam. We now invite Ms. Harvinder Kaur, Research Scholar, Department of Statistics, Punjabi University, Patiala, Punjab, India, to kindly present her paper. Madam, please.
Good morning, everyone. I'm Harvinder Kaur, Research Scholar, Punjabi University, Patiala, and today I'm going to present my work on analysis of a two-dimensional retrial queuing model with feedback having two parallel servers with equal service rate. Table of contents. Starting with introduction, we will go on with literature review, model description, solution of the problem, performance measures, graphical solution, and at last the references. Introduction. Queuing theory deals with the mathematical analysis of waiting in lines or queues. It is a branch of applied probability theory which utilizes the basics of stochastic processes. Queuing theory was originated by a Danish mathematician A.K. Erlang in 1909 with his pioneering paper The Theory of Probabilities and Telephone Conversations on the study of congestion of telephone traffic. A queuing system may further be described as one comprising of service facility of particular kind at which the units or customers arrive to receive service and depart from the system after successful completion of the service. The service is rendered as per predetermined rule. Retrial queues. This is the basic structure of a retrial queuing model. In retrial queues, if a customer on arrival finds the server free, it is served immediately, else it joins the orbit and retries for service after a random amount of time. After getting service, the customer departs from the system. Feedback retrials. This is the basic structure of a feedback retrial queuing model. In feedback retrials, if the customer on arrival finds the server free, it is served immediately, else it joins the orbit and retries for service after a random amount of time. Also, if the customer feels unsatisfied after service, it may join the orbit as a feedback customer, else it departs from the system. Literature review. Young and Templeton 1987, Ateljo and Gomes Corral 1999, Ateljo and Fallin 2002 are the early works done on retrial queuing models. Kumari 2011 studied feedback queuing models with the concepts of intermittently available servers, non-identical parallel servers, special servers, multiple servers, and correlated departures. Pegden and Rosenshine 1982 analyzed some new results for the MM1 queue in which a closed form solution with finite sums is obtained for the probability that exactly I number of arrivals j services occur over a time interval t. Singla and Kalera 2018a studied explicit time-dependent solution of a two-state retrial queuing model with two parallel servers. Singla and Kalera 2018b discussed performance analysis of a two-state queuing model with retrials. Model description. The detailed description of the present model is given as follows. The arrival process. The primary customers arrive at the system with Poisson process with parameter lambda. The retrial process. The secondary customers also follow Poisson process with parameter theta. The feedback rule. The unsatisfied customer joins the orbit with probability gamma, else departs from the system with probability 1 minus gamma. The service process. The service times follow exponential distribution with parameter mu. The input flow of primary calls, intervals between repetitions, service times are statistically independent. Two-dimensional state model definitions. Pij0 is the probability that there are exactly I number of arrivals, j number of departures, and servers are free by time t. Pijkt is the probability that there are exactly I number of arrivals, j number of departures from the system, and one or two servers are busy by time t. Pijt is the probability that there are exactly I number of arrivals, j number of departures from the system by time t, which is the sum of probabilities Pij0t, Pij1t, and Pij2t. Also, I should be greater than or equal to j. Initially, the following conditions are there. Differential equations governing the system are given in equations 1, 2, and 3. Using the Laplace transform, we obtain equations 4, 5, and 6. Solving equations 4, 5, and 6, we obtain the following equations. Taking the Laplace inverse of the equation 7 to 17, we get the time-dependent probabilities which are given in following equations. Performance measures. The Laplace transform of P bar I dot S is given below, and taking the Laplace inverse we get P I dot T is equal to e to the power minus lambda t to the power I divided by I factorial, which proves the basic assumption that primary arrivals follow Poisson process. The probability that exactly j customers depart from the system by time t is given below. Summing equation 7 to 17 over I and j, we get the sum equal to 1 by s, and taking the Laplace inverse, we get the sum equal to 1, which verifies our results. Now define Q and M as the probability that there are n customers in the orbit when m is equal to 0, 1, or 2 servers are busy at time t. When the server is free, it is represented by the probability Qn0t, which is given below. The number of customers in the orbit in this case are calculated as n equal to number of arrivals minus number of departures. When m servers are busy, it is represented by the probability Qnmt, which is given below, where m is equal to 1 or 2. The number of customers in the orbit in this case are calculated by formula n equal to number of arrivals minus number of departures minus m. Using above definitions in equations 1, 2, and 3 and letting mu is equal to 1, gamma equal to 0, the equations we get are 29, 30, and 31, which coincides the results 1, 2, and 3 of Fallin and Templeton 1997. Graphical solution. The probabilities against time are presented graphically through following figures. This is figure 1. Figure 1 depicts the plot of probabilities P000 and P110 against time t for the case when rho equal to 0.6, eta 0.5, and gamma 0.4. It is clear from the graph that the probability P000 rapidly decreases with time from initial value 1 at t equal to 0. The probability P110 increases in the beginning from initial value 0 at t equal to 0 and then decreases gradually. This is figure 2. Figure 2 shows the comparison between probabilities P510, 511, 512 when plotted against time 2 for rho equal to 0.6, eta 0.5 and gamma 0.4. Beginning with value 0 at t equal to 0, all the probabilities increases rapidly to their highest values and then decreases. It can be seen that the probability P512 is greater than P511, which is greater than P510 throughout. That is, the probability when both the servers are busy is greater than the probability when one server is busy, which is in turn greater than the probability when both the servers are idle or free. This is figure 3. The probabilities P211, 311, 411 and 511 for the case when rho equal to 0.6, eta 0.5 and gamma 0.4 are compared in figure 3. It is interpreted from the graph that in the starting the probabilities increases and then decreases. In general, it can also be concluded that the probabilities Pi01 take smaller value for higher I, where I is the number of arrivals. Conclusion. In the present work, we have obtained the time-dependent probabilities for exact number of arrivals and departures from the system for a two-dimensional retrial queuing model with feedback having two parallel servers with equal service rates. Performance measures and graphical solutions are also provided. References. Thank you.
Thank you, madam. We now invite Ms. Namisha Bansal, Research Scholar, Department of Statistics, Punjabi University, Patiala, Punjab, India, to kindly present her paper. Madam.
Good morning, respected teachers and my dear fellow researchers. I am Namisha Bansal from Department of Statistics, Punjabi University, Patiala. Today, I would like to take an opportunity to present a paper at International Conference of Mathematical Advances and Applications on the topic on existence of constant block sum PBIB designs under the esteemed supervision of Professor Davinder Kumar Garg. The blueprint for today's presentation would be starting from the introduction, constant block sum designs, construction of association scheme, then construction methodologies of PBIB designs, and last would be the references. As we all know, in the agricultural era, British statistician and geneticist named Sir R.A. Fisher discovered flaws in the ways experiments were performed, after which he gave the first blueprint of designing experiments in the book named The Design of Experiments. An experimental design makes controlled changes to input variables in order to gain maximum amount of information on cause and effect relationships with minimum sample sizes. Design of experiments has a lot of applications in the field of agriculture, cryptology, clinical research, animal husbandry, etc. Initially, as we all know, that experiments were conducted using complete designs, but later they were found to be unsuitable when the number of treatments to be tested increased. Hence, the need for incomplete designs was felt where each block receives only some of the selected treatments. At present, enormous number of incomplete designs are present, among which BIB designs are connected and variance balanced. But as it is known that BIB designs do not exist for every parametric combinations, because these designs are special designs and these designs are available in practical life very rarely. So by sacrificing the property of variance balance to some extent to control the variability within blocks, Bose and Nair in 1939 introduced new series of designs, namely partially balanced incomplete block designs. These designs are based on the construction of the association scheme. Now we would be discussing about constant block sum partially balanced incomplete block designs. As we have gone through the previous slides, it was said that in 1939, PBIP designs in general were discovered. But in 2019, Khatri came up with the idea of constant block-sum PBIB designs. He constructed PBIB designs using the famous 4x4 magic square named Parshavnath Yantram, which has enormous configuration leading to a sum of 34. As of now, equi-spaced quantitative treatments have been used, which has applications largely in biomedical experimentation. Repeated measure experimentation utilizes constant block-sum designs where the treatment levels are quantitative. It is desired that all units have to be exposed to the same constant cumulative dose at the end of the experiment. Now we are going to go ahead with the construction of the association scheme. To define our association scheme, we have used two concepts. One, concept of concentric circle reticles, and two, dimensional M-level segmented pyramids. A reticule or a reticule comes from a Latin word called reticulum, which means net. It is a pattern of fine lines in the eyepiece of a sighting device, for example, microscope, telescope, etc. Segmented pyramids have immense illusional characteristics which amuse human brains and is also often observed in architectural designs. The first association scheme is a 3-associate class association scheme using concentric circle reticles. For V treatments, which are equispaced in nature, where M are the number of concentric circle reticles and n is the n-tuple coordinate at a vertex of the figure. Then two treatments are first associates if they belong to same coordinate set or lie in the same position as that of the remaining concentric circles. Second associates if they lie on the same diameter, if they lie on the diameter opposite to the vertex or any one adjacent side of the concentric circles. And remaining treatments are said to be third associates. These are the parameters of the association scheme, which has V, NIs, and PIs. Next, we are going to talk about 3-associate class association scheme using 2-dimensional M-level segmented pyramids. For V equal to M plus N into M plus 2 into N by 2 treatments, where M represents the number of unit triangles in the base of the outermost circle and N is the n-tuple coordinate at a vertex. Then two treatments, say alpha and beta, are first associates if they lie on the same vertex set, second associates if both the treatments are non-adjacent to each other, and third associates if they are adjacent to one another. These are the general parameters of the association scheme discussed in the previous slide. Now, we are going to move ahead with the construction methodologies of PBIP designs. To go ahead with the construction methodology, we would like to discuss the potential parameters of a constant block-sum PBIP designs. Till now, Khatri has only discussed about the existence of constant block-sum PBIP designs using few examples, but nothing has been said about the existence or nothing has been proved about the theoretical existence as of now. So over here we have made an attempt to actually show that theoretically constant block-sum PBIP designs do exist and they have a large significance, and as we all know that practical evidences become more stronger by giving theoretical proofs to it. So for a design D with parameters V, B, R, K and lambda Q, assuming that treatments are equally spaced, then our main motive is to have the constant block sum either 0 or non-zero for a design D to check whether a constant block sum PBIP designs exist or do not exist. The sum of squares due to blocks is given by the equation. Variation in the block is 0 if and only if sum of squares due to blocks is 0. Solving the above equation for u equal to 1 reconfirms the non-existence of constant block sum BIB designs proved by Khatri in 2019 C. Now, our aim is to find constant block sum, possible parameters of constant block sum PBIB designs for an existing association scheme. We have derived a condition using which, by assuming the lambdas on our own, we can find rest of the parameters of a potential constant block sum PBIB designs. For a particular association scheme, constant block sum PBIB design exists if sum of squares due to blocks is 0. By substituting the value of k and solving for r, we get equation 1. Using 1 by taking various integral combinations of lambda q's and integral number of blocks, B can be found using VR is equal to BK equation. In this way, we can find all the parameters of the PBIB designs having a constant block sum for which B blocks of size K may exist. Now we are going to go ahead with the construction of the designs using the association schemes described in the previous section. First, we are going to take construction of 3 associate class design using concentric circle reticles. On each reticule, there are 4 points of intersection. The n-tuple coordinate of innermost circle have a constant sum and are found using n/2 set of paired sums of 4n treatments. For the subsequent circle points of the intersection are described by equation 2. Then, by choosing 2 blocks that are lying on each diameter, the remaining 2 blocks are the opposite quarters formed by the concentric circles. The general parameter of the design are given with the general formula for the constant block sum. For an illustration, we have taken an example by taking n equal to 4 and m equal to 2. The blocks of the design are given below with the parameters and the constant block sum. This is the association scheme that the design follows with the parameters. Next, we are going to discuss about the construction of 3 associate class design using 2-dimensional m-level segmented pyramids. For each m, the constructed figure is a 2m regular graph. The n-tuple coordinates having a constant sum found using n/2 sets of paired sums with retreatments. Blocks are formed by picking up a treatment alpha with its first associates along with any paired sum which are its second associates. Parameters of the constructed design are given below with the general formula of the constant block sum. We have explained the same thing using an example by taking n equal to 2 and m equal to 3. The diagram depicts an 3-level segmented pyramid. The blocks of the design have 15 blocks and are given with the parameters of the design and along with the constant block sum. This is the association scheme of the given design with the parameters of the association scheme. This is a table depicting list of some of the possible constant block sum PBIB designs for a given association scheme. There are enormous combinations. There are enormous combinations for these illustrations, but we have just depicted few, and the same was automated using our software. These were the references that we have used. Thank you.
Thank you, madam. We now invite Ms. Veena Shinde Dior, Assistant Professor, Bhavans H. Somani College, Chaupati, Mumbai, Maharashtra, India, to kindly present her paper. Madam, please.
Hello. Good evening, everyone. This is Veena Shinde Devi, Assistant Professor, Bhavans H. Somani College, Chaupati, Mumbai 7. First of all, I would like to thank the organizers of International Conference on Mathematical Advances and Applications 2020, the team of Red Talks Daily International, for accepting my abstract with the paper ID 2313 on a study of labelings of cycle-related graphs. Now, to introduce the topic, this is a topic from graph theory, wherein we study the different types of graphs, which is the collection of vertices and edges, which we denote by G, B, E. The graph is obtained by joining the vertices by edges. Now, a certain type of graph, which is called a cycle graph, it is a graph where the initial vertex and the final vertex is same, and we are joining all the vertices by a single line, that is the 2 points. There is no, as we have a cycle, so there is no coincidence or overlapping of any edges. So cycle is a continuous graph. After that, we have the labelings of graph. Now, labelings are the assignments of the numbers or integers to the vertices or edges, so that a particular labeling is satisfied by a particular graph. There are two types of labelings. One is the vertex labeling and one is the edge labeling. We label the vertex, and those vertex labelings induces the edge labelings. Similarly, if we label the edges, then the edge labeling induces the vertex labelings. After that, we have cycle related graphs. There are many cycle related graphs, of which some of them I have listed here. They are N cycle Cn, then the wheels Wn, which is the combination of the cycle graph Cn along with the single line graph with two vertices, that is K1. Then we have the N cone, we have the helm Hn, closed helm, a flower. We can also have a web, which is WTN, which is generalized web with Tn cycles. Then we have unicyclic graphs, that is the graphs with one cycle. We have the cycle with pk chords. Pk is the path with k edges. Then some more cycle related graphs are the cycle with parallel pk chord, shell type graphs, multiple shells. Then we have fans, cycle chains like C2m, N. Then a dragon, a tadpole, or kites. We also have book BN, where it is N book with M polygonal pages or the M+1 pages on it. Then we have C and T, which is 1-point union of T cycles of N length. With this, some more cycle related graphs are friendship graphs, triangular cacti, then triangular snakes, double triangular snakes, KCN snake. Then we have crown graph CNOK1, corona graph CNOH, where H is any graph and it is combined with CN. Then we have prisms, torrid grids, then symmetric product of cycles. So these are some of the cycle related graph. Now, while studying the cycle related graph, I found that there are many labelings, various labelings for these family of graphs, of which I was interested in learning more about the crown graph CNOK1. And while studying CNOK1, I came across some results on corona graph, which I would like to list. So corona graph labelings, here the vertices of the cycle CN are labeled with numbers, and K1 is the point which is joined to each vertex of CN. So we get a crown graph by joining a point to each and every vertex of the cycle. Crowns CNOK1 are graceful was shown by Bloom in 1970s. Grace further showed that an odd cycle with one or more pendant edges at each vertex is harmonious. Further, C2NOK1, an even cycle with one pendant edge attached to each vertex, is harmonious was proved by Liu and Zhang. Liu and Hegde, Horn, and Wu all proved that crowns CNOK1 are harmonious. M. Acharya and Bhatnayak have proved that crowns CNOK1 are minimally 2 equitable, minimally 2n equitable, minimally 4 equitable, and minimally n equitable. Crowns 3NOK1 are minimally 3 equitable, minimally 3n equitable, minimally n equitable, and minimally 6 equitable. Further, they also showed that crowns C5 OK1 are minimally phi equitable, minimally phi n equitable, minimally n equitable, and minimally 10 equitable. In general, or to generalize the result, they have shown further that crowns C2n plus 1 OK1 are minimally 2n plus 1 equitable. Further, Bloom used the term K equitable to describe the graph K equitable if the edge labels induced by the absolute value of difference of the vertex labels have the property that every edge label occurs exactly K times. Further, Bloom called a graph of order n minimally K equitable if the vertex labels are 1 to n and it is K equitable. Further, Barrentos calls a K equitable label to be optimal if the vertex labels are consecutive integers. Further, he calls this labeling to be complete if the induced edge labels are 1 to W, where W is the number of distinct edge labels. He proves that CMONK1 is optimal 2 equitable when M is even. C3ONK1 is complete 2 equitable when n is odd. C3ONK1 is complete 3 equitable for all n. CNOK1 is K equitable for every proper divisor K of size 2n. Further, Coming to the sequential graphs, Grace allows the vertex labels to range from 0 to q with no vertex label being used twice. He proved that odd cycles with 0 or more pendant edges are sequential. Liu and Zhang proved crowns C2n OK1 are sequential. Further, they have also shown that they are harmonious. Wu proved that crowns are sequential. He also proved that all even cycles with m pendant edges attached to each vertex are sequential. Further, Figueroa, Centona, Ishihama, and Mountaineer Battle proved that all cycles with m pendant edges attached to each vertex is sequential. Singh proved that CNOK2, CNOP3 are sequential for all odd n greater than 1. He also showed that CNOK2 is sequential for all odd n. Gayatri and Hemlata defines a graph as even sequential harmonious if G has an injective function from V to 0, 1, 2 up to 2 times mod E with the property that the induced mapping from E to the even edges, that is 2, 4, 6, 2 times mod E defined by F plus UV is equal to FU plus FV when FU plus FV is even. F plus UV is equal to FU plus FV plus 1 when FU plus FV is odd, is an injective function. They proved that C3ONK1 when n is greater than equal to 2 have even sequential harmonic labeling. Further, in 1970, Kodzik and Rosa defined magic valuation of the graph GV, E as the bijection from V union E to 1, 2 mod V union E, such that for all edges UV, f of u plus f of v plus f of u plus v is a constant called as magic constant. So they define the magic labeling, and they have shown that the CNOP2 are edge magic. CNOP2 have edge magic total labeling with magic constant as 27n plus 3 by 2. For n odd and at least 3, CNOP3 has edge magic total labeling with magic constant 39n plus 3 by 2. Further, Egnanarayan proved that crown CNOK1 have edge magic total labelings. He conjectured that for all n, CNOKN bar has edge magic total labeling. So these are the sum of the labelings. Even the corona CNOKM bar is also shown to be having super edge magic graph. Further, one more labeling, that is the prime labeling, was given to the crowns CNOK1, and it is shown that CNOPM is prime graph if n is equal to 3, and CNOPN is also a prime graph. So these were the sum of the results which were related to the corona graph or the crown graph CNOK1. These results can further be also developed, and more labelings for these cycle related graph can be studied, and some of the references from which I got these results are as seen on the screen. Thank you for patient hearing. I could complete only one type of graphs within 10 minutes. Thank you.
Thank you, madam. We now invite Dr. Vishal Kumar Sharma, Assistant Professor, Soban Singh Jira Campus, Almora, Mon University, Nainital, Uttarakhand, India, to kindly present his paper. Sir, please.
Hello to all. Myself, Dr. V.K. Sharma, Department of Physics, Kumar University, SSJ Campus, Almora. I am just going to deliver my talk, which is on the topic of tonic formulation of supersymmetry and dark matter candle. So these are the outlines of my talk, which is introduction, supersymmetry, octonic electroweak formulation, octonic formulation of the grand unified theory, octonic dark matter, supersymmetry dark matter, and then we have the result and discussion. These are the outlines of my talk. So we have the introduction. Introduction we are just going to hear. You can just see octonic when we are discussing here. You can just see here. For this, according to Horace theorem, we have the division algebra, which are namely the real, complex, quaternions, and these octonions here. So all the four division algebra are alternative with the total antisymmetric associator. Real number explains well with the classical Newtonian mechanism, while the complex number plays an important role for the explanation beyond the framework of the quantum theory and relativity. Real and complex number are limited only to the up to two dimensions, while the quaternions are extended to the four dimensions, one real and the three imaginary. On the other hand, the octonion represent eight dimensions, one real and the seven imaginary. Real and complex number are commutative and associative. Quaternions are associative but not commutative, while the octonions are neither commutative and nor associative but alternative. Quaternions are well connected with the familiar SU2 group and naturally unify electromagnetism and weak forces responsible for the electroweak SU2 cross U1 sector of the standard model here. Now, the octonion analysis plays an important role in the context of the various physical problems in the which are higher dimensional supersymmetry, supergravity, and the superextinction. On the other hand, octonions are also useful for the unification program strong interactions with the successful gauge theory of the fundamental interactions. You can just see here and a theoretical description of the electrons and quark structure for the hadrons are already been proposed by Gould and Goodsey in the context of the octonic quantum mechanics in the terms of the octonic Hilbert space. Keeping in mind the recent update of the theoretical physics, we have made the analysis for the octonions in the various field theories associated with the dimension and dark matter. In this context, we have the electroweak formulation, which is combining SU2 cross U1 here, while the other hand, grand unified GUT is by SU3 cross SU2 cross U1 here. So describing the octonic eight-dimensional space, we have the two quaternic space we have taken here, EM space and G space. We have re-examined the unified picture of EMG space in the terms of the octonic split formulation in the consistent manner. We have obtained the various field equation for the unified gravity electromagnetic interactions. Further, we have deconstructed the field equation of the hot and cold dark matter. And what is the basic significance between the cold and dark matter and OHDM and OCDM is the formulating of the structure of these two, because the velocity of the octonic hot dark matter cause it to wipe out on the small scale here. So this is the split octonion can be represented by this. You can just see here it is a linear combination of the unit elements octonions, which are represented by equation 1 here with their properties with the unit elements which are EA, E0, E1, E2, we satisfy the following multiplication rule represented by equation 2 here. In this we have the structure constant. This is the value 1 for this combinations. This is represented by equation 3 here, and we have the further octonic basic elements following relations are shown here in terms of the conical delta sigma equation 4 here. So this is the split octonion which is represented with equation 5 as well. Equation 6 also represents the multiplication certain multiplications rules, and equation 6 corresponds to this set of the multiplications rule followed by split octonions. Now we come to the octonic electroweak formulation, as we have discussed here electron gauge formulation, which is represented by U1 cross SU2 in terms of the split octonion representation. We have further electric and the magnetic charges. Electric charge A mu and magnetic charge are represented by B mu. They are in terms of the expanded in terms of the quaternions. You can just see here by shown by equation 7 here, where these are the corresponding A0 and B0 mu corresponding for the electric and magnetic 4 vector potential for the diodes for the U1 gauge formulations here. So we have The double fold degeneracy of the SU2 U1 cross SU2 gauge theory is determined by equation. You can just say defined by equation 8. While the equation 9 is the U1 cross SU2 gauge field distance diamond in terms of 2 cross 2 John vector representation. It is number compact form. It is represented by G mu. G mu is corresponding to the abelian and non-abelian U1 cross SU2 in terms of presence of the electric charges. While we have the magnetic charges are represented by equation 2 here is structured due to the presence of the magnetic monopoles here. Operating d mu, this on g mu, we have equation 13, which is corresponding to the leading to the j mu. J mu is what? It is the U1 cross SU2 form of the octonic gauge current, similar to the normal V current for the diodes, and which is also leading to the equation 15. Equation 15 is the split octonic formation of electroweak gauge theory in the consistent, compact, and simpler notifications as well. And here you just see here gauge symmetry, which is the standard internal symmetry representing the standard. You can just say here model. You can just see this is corresponding to a standard model. The smallest simplest Lie group which contains the standard model and upon which the first grand unified theory is based upon. This is SU3 cross U1, SU2 cross U1 here. And what is the equation 16? Equation 16 is the gauge field for the generalized field of the diodes here. Now, equation 16 is also 2 cross 2 John vector represent a split of nonunions, which is further reducing to equation 18, while we have equation 19, which is the equation taking the form in SU3 cross SU2 cross U1, which is for octonic gauge field distance for the diodes as well. We have this, we getting equation 20 here, and which may be further reduced in terms of the compact notification of the octonic form as d mu, g mu. This is j alpha nu, which is corresponding to the John vector representation of the split octonions, which is corresponding to the octonic gauge current. Now, this is which is leading to Newtonian current by equation 23, which is analogous to the, you can just say the generalized, you can just say generalized continuity equations here. For this is in the grand unified theory. Now we just come to the dark matter. Dark matter, it is also the hypothesized matter which is present in the universe, and almost a large part of the universe is covered by this dark matter. And mass energy of the universe is to 4.46%, which is consisting the ordinary matter, and dark matter about 23% is composed to the dark matter. 72%, as you know, this is the dark energy. Strands are component distributed or almost uniformly in space and with the energy density not evolving slowly evolving with the time. On the other hand, non-baryonic form of the octonic dark matter is evident through its gravitational effects only. So each in the units in the critical density, which is here h is it is the Hubble's constant cosmological parameter. G is the Newton's gravitational constant here. Experimental values results have required that the best current values for the matter and energy density are represented by this equation, and the range of the density parameters in terms of the Hubble as well as the data, this is the corresponding to this value. The matter density, it is combination of baryons plus dark matter. Dark matter can be hot and cold depending on the just or whether it was a relative state or not in the universe. So we can have analyze the hot and cold dark matter in terms of the split octonions. So the equation 25 is describing the octonic hot dark matter density. So we can just have hot dark matter as represented by equation this 26, and this is the field distance corresponding to the hot dark matter is this equation 27 also corresponding, and we have also this SDM from hot dark matter in terms of the split octonic form. This is equation 28 and 29 are sigma for hot dark matter. So on the other hand, you can just see here this supersymmetric dark matter. Supersymmetry is a symmetry that relates the fermionic and bosonic degrees of freedom. It therefore predicts new symmetric particles which are partners of all the known particles and differ in the space by half a unit. In addition, the total number of bosonian and fermionic degrees of freedom must be equal here. The supersymmetric particles carry with them quantum numbers with the exception of the spin identical to those of the ordinary particles partners here. From the above discussion of the supersymmetric dark matter, we have known that LSP, that is supersymmetric particles, and dark matter, which this is the topic here, would normally be a new stable particle. Here, it often happens that an extension of the standard model will lead to the new stable particle. The LSPs would be have very differently from the baryons since their interactions are typically electroweak with the low energy cross sections in the 10 minus 38 centimeter square range. They do not undergo nuclear reactions, and for luminous star they might be the dark matter. So we have the resultant discussion. Octonic hot and cold dark matter may be expressed in the terms of the simple and complex octonic representation. Matter density of the cold and dark matter is greater. Cold dark matter is greater than the hot dark matter. There exists more cold dark matter than the hot dark matter, which is the supported by the octonic field equations. And the dark matter particles are spread more or less uniformly throughout the galaxy, and we are moving through them as the Earth moves here. So thank you. Thanks for your question, and thanks to Sir Dr. Ratnakar sir for giving me opportunity to present my lecture here. So thank you. Thanks to all of you. Thanks for your presence as well. Thank you.
Red Talks. Thanks to all the speakers and the chairpersons who have contributed to this International Conference on Mathematical Advances and Applications 2020. Red Talks also congratulates all the delegates who have presented their papers. We now invite Dr. Vijay Kumar, Manavarachna International Institute of Research and Studies, Haryana, to receive his invited talk certificate. Thank you, sir. We now invite Dr. Srinivas Rao Tota, Adama Science and Technology University, Ethiopia, to receive his invited talk certificate. Thank you, sir. We now invite Dr. Selva Ganeshan S., JJ College of Engineering and Technology, Tiruchirappalli, to kindly receive this certificate of invited talk. Thank you, sir. We now invite Dr. Ayaz Ahmad, National Institute of Technology, Patna, to receive his invited talk certificate. Thank you, sir. We now invite Dr. M. Iqbal Jilani Bhatt to receive the participation presentation certificate.